Approximately 232 million years ago, during the early Triassic period, Earth's atmosphere entered a state that has no precise parallel in the modern world. The planet was warm. Surface temperatures in equatorial regions routinely exceeded 35 degrees Celsius, and the hydrological cycle, the continuous process by which water evaporates, condenses, and falls again, had accelerated far beyond its current parameters. Evaporation rates over shallow inland seas were extreme. Moisture loading in the lower atmosphere was dense and persistent. The conditions required for precipitation were met not seasonally, but continuously across vast geographic regions. Rain fell, and it continued to fall, not for days or weeks or seasons, but across timescales measured in geological strata, layer upon layer of sediment, each one a record of water that never stopped arriving. This was the world that living creatures already occupied. The land surface of early Triassic Earth was not empty. Life had survived the end Permian extinction event approximately 252 million years ago, the most severe mass extinction in the planet's history, during which an estimated 90 to 96% of all marine species and roughly 70% of terrestrial vertebrate species disappeared entirely. What remained were the survivors, small, opportunistic, physiologically resilient organisms that had endured conditions of intense heat, oxygen depletion, and ecological collapse. By the early to mid-Triassic, these lineages had begun to diversify again. The land was being reoccupied cautiously by animals that bore little resemblance to the dominant fauna that had come before. Before we continue, take a moment to consider where you're watching, from which country, and how far removed it is from a world where the rain did not stop for millions of years, reshaping the planet in slow and relentless ways. If these distant eras draw you in, consider subscribing to continue the journey. It's always remarkable to sense how far these stories travel. Dim the lights, settle into the quiet, and let the modern world fade beneath the steady sound of endless rainfall, falling across ancient forests, rising seas, and a planet slowly changing under darkened skies. Among the most significant of these early recolonizers were the temnospondyls, a broad group of large semi-aquatic amphibians with flattened skulls, wide jaw structures, and body plans optimized for life at the boundary between water and land. Some species within this group reached lengths of 2 to 3 meters. Others, in later periods, would grow considerably larger. They were predators by functional design, low-bodied ambush hunters that relied on proximity to standing water for reproduction, thermoregulation, and pursuit of prey. In a world where water was accumulating faster than drainage systems could disperse it, these animals were positioned with considerable ecological advantage. The environments they inhabited were not forests in any sense recognizable today. The great coal swamp forests of the preceding Carboniferous period had long since collapsed. What had replaced them, in the wake of the end Permian crisis, were recovering ecosystems fragmented, unstable, dominated by early seed plants, ferns, and low-growing vegetation that could tolerate waterlogged soils and interrupted sunlight. In regions where rainfall was becoming chronic, the soil itself was transforming. Organic matter accumulated faster than it could decompose in saturated conditions. Drainage gradients flattened as water tables rose. Lowland areas that might once have dried seasonally were remaining wet indefinitely. The mechanics behind this prolonged wet phase are traceable to several intersecting geological and atmospheric processes. The Triassic period began with the supercontinent Pangaea largely intact, a single continuous landmass stretching across much of the planet's surface. The interior of this landmass was prone to extreme thermal conditions. Without the moderating influence of surrounding ocean, continental interiors experienced intense heat during warmer periods. This heat drove powerful convective systems in the atmosphere above, pulling moisture inward from coastal margins and generating storm activity over regions that might otherwise have remained arid. At the same time, elevated volcanic activity, a continuation of processes associated with the end Permian event, was releasing significant quantities of carbon dioxide and water vapor into the atmosphere. Water vapor is itself a greenhouse gas. Its presence in elevated concentrations strengthened the thermal forcing that was already intensifying the hydrological cycle. The atmosphere held more moisture. Clouds formed more readily and persisted longer. When precipitation occurred, it occurred at higher intensities and over longer durations than contemporary baseline rates. Current paleoclimate models suggest that certain intervals within the Triassic and extending into the earliest Jurassic were characterized by precipitation regimes dramatically wetter than any experienced in the modern era. The specific event, sometimes referred to as the Carnian pluvial episode, dated to approximately 232 to 234 million years ago, represents one of the most clearly documented of these intervals. Sedimentary evidence from multiple continental regions, including what are now Europe, North America, and parts of Asia, records a marked and sustained increase in rainfall during this period. Paleosols, ancient preserved soils, show characteristics consistent with prolonged waterlogging. River channel deposits widen significantly in the geological record, indicating higher discharge volumes over extended timeframes. For the creatures living through this transition, the environmental shift was not an abstract geological event. It was the direct physical context of every behavioral and physiological decision their biology allowed them to make. Consider the functional reality of a world where standing water was not a seasonal feature of the landscape, but a permanent one. Floodplains that had previously dried and recovered between wet cycles were now remaining inundated. Root systems of established plants drowned when oxygen could no longer reach them through saturated substrate. Trees fell. Shorelines dissolved into broad, shallow marshes extending for distances that no individual animal could perceive as having boundaries. The land and the water were no longer clearly separated. They were blending into a single, vast, intermediate environment, neither fully terrestrial nor fully aquatic, that would persist for a geologically significant duration. The temnospondyls moved through this environment with functional competence. Their laterally compressed limbs and sprawling gait, a body plan inherited from earlier amphibian lineages, were well suited to navigating shallow water and soft substrate. Their skin, like that of modern amphibians, required moisture for basic physiological function, including respiration through cutaneous gas exchange. A world that was becoming progressively wetter was, in the most immediate biological sense, a world that was becoming more hospitable to them. Prey animals, early insects, smaller vertebrates, fish persisting in expanded freshwater systems were present in sufficient density to sustain predator populations. The swamps provided concealment. The shallow, murky water provided ambush cover. Evidence recovered from Triassic fossil deposits in locations including the Karoo Basin of southern Africa, the Chinle Formation of what is now the American Southwest, and marine sequences in the Tethys region converges on a picture of ecosystems under significant stress but not yet collapsed. Species richness in some terrestrial groups declined during the onset of the wet phase. Certain plant communities were replaced by others more tolerant of waterlogged conditions. But life continued. Animals fed, reproduced, and died in environments that were changing on timescales far too slow for any individual organism to detect. Above these flooded lowlands, the sky was rarely clear. Cloud cover during intervals of peak rainfall during the Carnian pluvial episode would have been extensive and persistent. Cumulonimbus systems, the deep convective storm structures responsible for heavy precipitation form when warm, moist air rises rapidly through the lower atmosphere and reaches altitudes where it cools and condenses. In an atmosphere with elevated moisture loading and strong surface heating, the conditions for such systems are met repeatedly and continuously. Lightning discharge rates in such environments would have been substantially higher than those observed in modern tropical storm systems. Thunder would have been a near constant feature of the acoustic environment. The light reaching the surface through this persistent overcast would have been diffuse and reduced in intensity. Photosynthetically active radiation, the portion of the solar spectrum usable by plants for energy production, would have been attenuated significantly on overcast days, and overcast days were the norm rather than the exception. Plant communities adapted over time to lower light availability, favoring shade-tolerant species and shifting the composition of ground-level vegetation. Animals that relied on solar radiation for thermoregulation, as many reptilian lineages do, faced physiological challenges in maintaining adequate body temperatures. Amphibians, with lower metabolic requirements and greater tolerance for temperature variation, were comparatively less constrained by this condition. The soundscape of these environments, if it could be reconstructed, would have been defined by water, rain on broad-leaf surfaces, the low continuous sound of runoff moving across saturated ground, the irregular percussion of dripping through layered canopy, wind-driven precipitation against standing water. These were not silent environments. They were acoustically dominated by the very process that was reshaping them, the continuous arrival of water from above, driven by atmospheric systems that had been set in motion by forces operating at a planetary scale, and that would continue operating at that scale for longer than most lineages of animals alive at the time would survive. The geological and biological record of this period encodes a world in the process of fundamental reorganization. The dominant ecological relationships of the Permian were gone. The dominant ecological relationships of the later Triassic and Jurassic had not yet fully formed. What existed in between was a transitional biosphere, experimentally diverse, ecologically unstable, and saturated, in the most literal sense, with water. The animals living within it were not aware of their transitional status. They were responding to immediate environmental pressures, where to find prey, where standing water was deep enough to retreat into, where the substrate was firm enough to support movement. That the rain continued was not, to them, a phenomenon with a name or a duration. It was simply the condition of the world as they experienced it, the permanent grey above, the dark water below, and the space between them occupied by creatures that had, for the moment, found ways to endure. By the middle of the Carnian pluvial episode, the landscape of Pangaea's equatorial and mid-latitude regions had undergone a transformation measurable not merely in ecological terms, but in physical geography. River systems that had previously operated within defined channels were losing their banks. Sediment cores extracted from Triassic Age deposits in the Alpine region of Europe and the Germanic Basin record a distinct and sustained shift in depositional patterns from the red, oxidized sediments characteristic of drier conditions to the gray and dark organic rich layers that form in persistently waterlogged, low-oxygen environments. This transition in the rock record is not gradual in the way that most geological changes are gradual. It is comparatively abrupt, occurring across what geologists estimate to be a relatively narrow stratigraphic interval, suggesting that the shift toward wetter conditions happened quickly by geological standards perhaps across tens of thousands of years rather than millions. The ecosystems that developed within this expanding wet zone were structurally unlike the recovering post-Permian landscapes that had preceded them. Vegetation density increased where light still penetrated. Ferns and horsetails plants with deep evolutionary histories and high tolerance for wet substrate spread across lowland regions and formed dense, layered ground cover. Early coniferous trees, members of lineages that had survived the end Permian event, grew in elevated areas where drainage was sufficient to prevent root suffocation. But in the lowlands, where water tables had risen to or above the surface, the dominant ecological structure was not forest. It was marsh expansive, poorly drained, biologically productive, and increasingly dark. The darkness was a function of multiple interacting conditions. Persistent cloud cover reduced direct solar input at the surface. Dense vegetation in areas where plants could still grow further attenuated the light reaching the ground. Suspended particulates in standing water, fine clay, decomposing organic matter, microbial material reduced water transparency to near zero in many locations. An animal moving through the flooded lowlands of mid-Triassic Pangaea would have operated in an environment where visibility, whether through air thick with mist and rain or through black, opaque water, was severely limited at most times. This had direct consequences for predator-prey dynamics. Ambush predation, a strategy that depends on concealment and proximity rather than pursuit speed, was functionally favored in environments where detection distances were short and cover was abundant. The temnospondyle amphibians that dominated many of these ecosystems were, anatomically, ambush predators. Their skulls were wide and dorsiventrally flattened, placing the eyes high and allowing them to remain nearly fully submerged while maintaining a line of sight above the waterline. Their jaws were equipped with numerous small conical teeth suited to gripping prey that could not easily be chewed fish, smaller tetrapods, invertebrates, and swallowing it largely whole. They did not pursue. They waited. In the flooded jungles of the mid-Triassic, waiting was an effective strategy. Prey animals had limited options for detecting a predator that was itself nearly indistinguishable from the submerged substrate. A temnospondyle lying motionless in shallow, turbid water over dark organic sediment presented almost no visual signature. Movement, when it came, was rapid and committed a lunge driven by powerful axial musculature, closing the distance between predator and prey in a fraction of a second. Beyond the amphibians, the flooded ecosystems of this period supported a broader community of animals whose diversity reflected the ecological opportunities created by expanding wetland habitats. Early archosaurs, the reptilian lineage from which both crocodilians and dinosaurs would eventually descend, were present in these environments, though not yet dominant. Many early archosaur species were semi-aquatic in their habits, occupying ecological roles comparable to modern crocodilians. Low profile, opportunistic predators capable of moving between water and land with reasonable efficiency. Their scales and relatively impermeable skin gave them a physiological advantage over amphibians. In one specific respect, they were not dependent on external moisture for cutaneous respiration and could therefore exploit drier microhabitats when these existed, or survive temporary exposure to air with less immediate physiological cost. The coexistence of large amphibians and early archosaurs in these environments was not a stable equilibrium relationship. It was a competitive one, shaped continuously by the specific conditions of each local habitat. In the deepest, most persistently, flooded areas broad, shallow lakes and marshes where water depth precluded easy terrestrial movement, temnospondyls held the advantage. Their body plans were optimized for exactly these conditions. In areas at the margins of flooding where substrate alternated between wet and merely damp, early reptilian lineages could move more effectively and access food resources that amphibians could not readily exploit. The flooding itself was therefore not acting uniformly on all species. It was acting as an ecological filter, systematically expanding the zone of habitat favorable to water-tolerant lineages while contracting the zone available to those requiring drier conditions. Over thousands of generations, this filter was shifting the competitive balance of entire faunal communities. Insects occupied a distinct but ecologically significant position within these flooded jungle ecosystems. The Triassic period did not replicate the extreme insect gigantism of the Carboniferous, during which atmospheric oxygen concentrations near 35% had permitted dragonfly relatives with wingspans exceeding 65 centimeters to exist. Triassic oxygen levels were lower and less favorable to such extreme scaling. Nevertheless, insect diversity during the Triassic was substantial, and the humid, vegetation-dense environments created by persistent rainfall provided ideal conditions for many groups. Decomposing plant material abundant in any waterlogged ecosystem where dead vegetation accumulates faster than aerobic decomposition can process, it supported large populations of detritivorous insects. These, in turn, supported predatory insect lineages as well as the small vertebrates that fed upon them. The food web architecture of these environments was therefore built from the bottom up on decomposition. Waterlogged conditions inhibit the activity of aerobic decomposer organisms, bacteria, and fungi that require oxygen, causing organic matter to accumulate rather than cycle efficiently. This accumulation formed the thick, peat-like deposits that would, over geological time and under pressure, become coal. The same conditions that were building future coal seams were, at the time of their formation, structuring entire ecosystems around the slow breakdown of plant matter in anoxic water. Massive rivers draining these wetland systems were themselves ecological features of considerable significance. Paleochannel evidence that preserved traces of ancient river courses identifiable in sedimentary rock indicates that river systems during the Carnian pluvial episode were broader and carried higher sediment loads than their predecessors or successors in the same regions. Discharge volumes were elevated by continuously high precipitation across large catchment areas. These rivers did not behave like modern temperate rivers, with seasonal flood peaks and low water periods. Evidence suggests they maintained high flow rates with reduced seasonal variation, behaving more like rivers in modern per-humid tropical regions where rainfall is distributed relatively evenly across the year. Where these rivers reached lower elevations and flatter terrain, they spread. Channels bifurcated into distributary networks. Floodplains became permanent rather than episodic features. Entire landscapes that might, under different climatic conditions, have supported terrestrial vegetation were converted into braided river systems and associated wetlands extending for hundreds of kilometers in every direction. For large animals, this meant that movement across the landscape required navigating water as a near-constant obstacle. Migration between habitat patches, a behavioral strategy that many terrestrial vertebrates use to exploit seasonal resources, became more difficult as the contiguous dry land connecting those patches disappeared. Populations became more isolated. Gene flow between geographically separated groups was reduced. Over sufficient timescales, isolation drives divergence, and divergence, under strong environmental selection pressure, accelerates speciation. The flooding was not only killing some lineages, it was, simultaneously, creating the conditions under which new ones would form. The storms that maintained this system were not random or irregular events. They were the predictable output of an atmospheric engine running on abundant fuel. Warm ocean surfaces. Sea surface temperatures in the Tethys Ocean during this period are estimated to have reached 36 degrees Celsius or higher in equatorial regions. Evaporated water continuously into the lower atmosphere. This moisture was transported inland by prevailing wind patterns and lifted by orographic barriers and convective heating over the dark, heat-absorbing surfaces of the continent. Once lifted, it condensed and fell. The cycle completed itself and began again, not over days, but continuously, maintained by the thermal gradient between a warm ocean and a warm but convectively active continental interior. Lightning struck repeatedly across the flooded canopy. Each discharge carrying currents estimated in modern storms at between 5,000 and 200,000 amperes ignited fires where dry fuel existed. But in the persistently wet conditions of the flooded jungles, fire could not sustain itself. The electrical energy dissipated into saturated wood, standing water, and wet soil without propagating. The storms killed trees directly through strike damage, creating gaps in the canopy that were quickly colonized by light-hungry ferns and low vegetation. The forest, where it existed, was perpetually disturbed, perpetually recovering, and perpetually being disturbed again. This was not a stable ecosystem approaching equilibrium. It was a system under continuous, energetic forcing, maintained far from any resting state by the relentless input of water and energy from above. The creatures within it were not passive inhabitants of a fixed environment. They were organisms in continuous physiological and behavioral response to an environment that was itself in continuous motion. The atmosphere is not a passive medium. It is a fluid system, dynamic, stratified, and capable, under the right thermodynamic conditions, of organizing itself into structures of extraordinary scale and sustained intensity. During the peak intervals of the Carnian pluvial episode, the atmospheric conditions over Pangaea and the surrounding Tethys and Panthalastic oceans met the criteria for storm organization at a magnitude that has no direct equivalent in the modern observational record. Understanding what this meant for the surface of the Earth requires understanding the mechanics of how water moves through air and what happens when those mechanics operate without the moderating constraints that define contemporary climate. Water enters the atmosphere through evaporation. The rate of evaporation is governed primarily by surface temperature and the vapor pressure deficit, the difference between the amount of moisture the air currently holds and the maximum it can hold at a given temperature. When sea surface temperatures are elevated, evaporation rates increase non-linearly. Current estimates place Tethys Ocean surface temperatures during the Carnian at approximately 34 to 36 degrees Celsius in equatorial regions, values that significantly exceed the 28 to 29 degrees Celsius threshold, above which modern tropical cyclone intensification typically occurs. At these temperatures, evaporative flux into the lower atmosphere was substantially higher than any sustained rate observed in the modern ocean. The atmosphere above the Tethys was, in the most functionally precise sense, being loaded with water continuously and at scale. When moisture-laden air is forced upward by convective heating, by orographic lifting over elevated terrain, or by the convergence of air masses with different thermal properties, it cools at a predictable rate. As it cools, water vapor condenses around atmospheric particulates, forming cloud droplets. When those droplets aggregate sufficiently, they fall as precipitation. The energy released during condensation, latent heat, warms the surrounding air, causing it to rise further, drawing more moist air upward from below. This feedback mechanism is the engine of deep convective storm systems, and it operates more powerfully when the initial moisture content of the ascending air is higher. During the Carnian pluvial episode, this engine had abundant fuel. Convective systems forming over the warm Tethys would have been capable of reaching altitudes in excess of 15 to 18 kilometers, penetrating the tropopause and injecting water vapor directly into the lower stratosphere. At these altitudes, the dynamics of the storm system interact with large-scale atmospheric circulation patterns, allowing organized weather systems to persist and propagate across distances measured in thousands of kilometers. The storms were not local events. They were continental-scale phenomena, sustained by oceanic evaporation and organized by the thermodynamic structure of an atmosphere operating under conditions of extreme moisture loading. Some researchers have proposed, in the context of extreme paleoclimate events, the theoretical framework of hypercane formation, storm systems analogous to modern hurricanes but of significantly greater intensity and spatial extent, potentially forming when ocean surface temperatures exceed approximately 50 degrees Celsius. Whether true hypercanes formed during the Carnian remains a matter of scientific debate, and current evidence does not conclusively support their occurrence during this specific interval. However, the general principle that elevated sea surface temperatures produce more intense and more persistent storm systems is well established in atmospheric physics and is directly applicable to Carnian conditions. The storms that existed were not hypercanes in the theoretical extreme sense, but they were larger, more energetic, and more persistent than any storm system in the modern Atlantic or Pacific basins. The physical consequences of this precipitation regime on the land surface were extensive and geologically legible. Rainfall intensity, the rate at which water arrives at the surface per unit time, determines the capacity of that water to erode exposed substrate. When rainfall intensity exceeds the infiltration capacity of the soil, water runs off across the surface rather than percolating downward. This surface runoff carries suspended sediment, and the more intense the rainfall and the less vegetated the surface, the greater the sediment load transported. In regions where vegetation had been killed by flooding or where newly exposed surfaces existed landslides, fault scarps, riverbanks undercut by high discharge erosion rates during Carnian rainfall events would have been extreme. Sedimentary evidence from Triassic age formations in multiple regions supports this interpretation. The thickness and grain size distribution of clastic sediment layers deposited during the Carnian interval indicate high energy depositional events, rapid emplacement of coarse material consistent with flash flooding, and high discharge river behavior. In some sequences, these coarse layers alternate with finer-grained organic-rich intervals, reflecting the episodic nature of the most intense precipitation events superimposed on a background of continuous moderate rainfall. The landscape was being physically rearranged. Highlands eroded, valleys filled with sediment, coastlines shifted as river systems delivered massive quantities of terrigenous material to shallow marine environments. The redistribution of water across the continental surface was altering not only local topography but regional hydrology at a fundamental level. River catchments expanded as rainfall extended into previously arid interior zones of Pangaea. Drainage divides the topographic boundaries, separating one river system's catchment from another, migrated as erosion differentially lowered terrain on one side or the other. Rivers captured the headwaters of adjacent systems, reorganizing entire drainage networks across timescales of tens of thousands of years. What had been a river draining toward one coastline might, following a period of sustained erosion and headward capture, drain toward a different ocean entirely. In the lowest-lying regions of the continental interior, water had nowhere to go. Endorheic basins closed drainage systems with no outlet to the sea filled progressively. Shallow inland seas formed where none had existed in the immediately preceding dry interval. These were not marine environments. They were freshwater or slightly saline lakes of enormous lateral extent but relatively shallow depth, broad, flat bodies of water occupying topographic depressions that had been filled by runoff faster than evaporation could remove the water. In an atmosphere where evaporation was perpetually returning to the surface as rain, these inland bodies were effectively permanent features of the landscape for as long as the precipitation regime persisted. The optical consequence of this water distribution, the reflectivity, or albedo, of vast shallow water surfaces would have interacted with the energy budget of the lower atmosphere. Water surfaces reflect less solar radiation than dry land covered with light-colored soil or rock. Darker surfaces absorb more energy, warming the air above them and reinforcing convective activity. The expansion of surface water area was therefore not a neutral event with respect to the atmosphere. It was a feedback increasing the thermal energy available to drive further convection and further precipitation. The system was, to a degree, self-reinforcing. Lightning discharge during peak storm activity over Pangaea would have been a near-continuous atmospheric phenomenon across large regions. Modern cumulonimbus storm cells produce lightning at rates ranging from 1 to several discharges per minute. Continental-scale storm systems, organized into mesoscale convective complexes spanning hundreds of kilometers, produce lightning continuously across their entire footprint. During the most active intervals of the Carnian wet phase, the total lightning discharge rate across Pangaea's storm-active regions may have been orders of magnitude higher than current global rates, which average approximately 40 to 50 lightning strikes per second across the entire planet. The energy deposited by this lightning into the terrestrial environment was not trivial. Strike damage to trees contributed to canopy disruption. Nitrogen fixation driven by lightning discharge, a process in which the extreme temperatures of a lightning channel force atmospheric nitrogen and oxygen to combine, producing nitric oxides that fall to the surface in rainfall and become biologically available, would have delivered substantial quantities of fixed nitrogen to already nutrient-saturated wetland soils. This nitrogen input supported microbial productivity and, through food web linkages, the broader biological communities dependent on microbial production at the base of the ecosystem. Mountain ranges presented particular interactions with these storm systems. When moisture-laden air encounters elevated terrain, it is forced upward, cooling and precipitating on the windward slope, a process called orographic enhancement. The leeward side of mountain ranges, by contrast, receives comparatively less precipitation as the descending air warms and dries. During the Carnian, the orographic effects of Pangaean mountain systems, including the precursors of what are now the Appalachians and the Variscan ranges of Europe, would have created strong precipitation gradients across short distances. Windward slopes received rainfall at extreme rates. Leeward zones were comparatively drier, though still wetter than modern analogues given the elevated background moisture of the entire atmosphere. Entire mountain faces were being actively sculpted by this precipitation. Runoff on steep slopes achieved velocities sufficient to mobilize large clasts, boulders, and cobbles transported downstream by floodwaters and deposited in coarse alluvial fans at the base of ranges. The fan deposits of Triassic age preserved in several geological formations record exactly this process. Coarse, poorly sorted material emplaced rapidly by high-energy flows from elevated source terrain, grading downslope into finer sediment deposited by slower-moving water on the adjacent plains. The mountains were not disappearing instantaneously. Erosion, even intense erosion, operates on timescales of millions of years when measured against the full height of a mountain range. But the rate of denudation, the lowering of surface elevation through erosion, was measurably elevated during the wet phase. Rock that had been stable for millions of years was being mobilized, transported, and redeposited. The continental surface was in a state of accelerated physical flux, driven not by tectonics in this instance, but by water falling continuously from a sky that showed no reliable indication of clearing. Among the vertebrate lineages that inhabited the waterlogged landscapes of the Triassic, none were more thoroughly adapted to the conditions of persistent flooding than the large amphibians. The temnospondyls, a group with origins extending back into the Carboniferous period more than 300 million years ago, had survived the end Permian extinction and continued diversifying into the Triassic, producing some of the largest semi-aquatic predators the terrestrial record preserves. These were not marginal creatures occupying peripheral ecological roles. In the flooded ecosystems of the mid-Triassic, they were apex predators across broad regions, and their body plans, refined over tens of millions of years of amphibian evolution, were functionally well matched to an environment defined by shallow water, low visibility, and abundant aquatic prey. The largest temnospondyle genera known from Triassic deposits include animals of considerable size. Mastodonsaurus, recovered from Middle Triassic formations in what is now Germany and other parts of Europe, reached estimated body lengths of approximately 4 to 6 meters, with a skull alone measuring up to 1.25 meters in length. The skull architecture of this animal reflects its ecological strategy precisely. It was broad, flat, and heavily constructed, with large temporal fenestrae indicating powerful jaw-closing musculature. The orbit's eye sockets were positioned dorsally, near the top of the skull, consistent with an animal that spent significant time submerged with only its eyes and nostrils at or above the waterline. The tooth arrangement included large, interlocking fangs at the front of the jaw, capable of securing struggling prey, supplemented by smaller teeth along the jaw margins for grip retention. The ambush strategy employed by these animals was not merely a behavioral preference, it was a physiological necessity shaped by the energetic constraints of amphibian metabolism. Amphibians are ectothermic. They do not generate body heat internally at rates comparable to mammals or birds, and their metabolic rate at rest is substantially lower than that of endothermic animals of equivalent mass. This low resting metabolism means that amphibians require less food per unit time than comparably sized endotherms, but it also means they cannot sustain high-energy activity, pursuit predation, for instance for extended durations. A large temnospondyle could not chase prey across open ground the way a similarly sized theropod dinosaur might. It could, however, remain motionless in shallow water for extended periods at very low energetic cost, and then execute a rapid, powerful strike when prey came within range. In the flooded jungles and marshes of Carnian Pangaea, this strategy was highly effective. The turbid, dark water that characterized most standing water bodies in these environments severely limited the ability of prey animals to detect a submerged predator at any meaningful distance. Prey species, fish, smaller amphibians, early reptiles moving through shallow water, invertebrates would routinely approach within striking distance without any indication of the predator's presence. The strike itself, when it came, was driven by a rapid lateral sweep of the head combined with a short-distance lunge of the entire body, closing a gap of perhaps 1 to 2 body lengths in a fraction of a second. Prey capture was essentially complete before any evasive response could be initiated. The reproductive requirements of these animals both reflected and reinforced their dependence on permanent water. Like modern amphibians, temnospondyls almost certainly reproduced by laying eggs in aquatic environments. Their larvae, the juvenile stage between hatching and metamorphosis into the adult form, were obligate aquatic organisms, gill-breathing, and incapable of surviving in terrestrial conditions. In a landscape where standing water was ephemeral or seasonal, a population of large amphibians would face periodic reproductive failure whenever water bodies dried before larvae completed development. In a landscape where standing water was permanent and widespread, this constraint was removed. Every flooded lowland was a potential breeding site. Every year was a viable reproductive year. The demographic consequences of this shift were significant. Populations that might otherwise have been limited by the availability of suitable breeding habitat could expand into newly flooded regions without the reproductive bottleneck that dry conditions imposed. Fossil evidence from Triassic formations preserving temnospondyle material sometimes shows high densities of individuals' bone beds containing multiple specimens of similar size, interpreted as mass mortality events, possibly associated with drought within the wet phase or localized drying of water bodies. These assemblages, while representing death events, also indicate that population densities of large amphibians in favorable habitats were substantial. Oxygen availability in these waterlogged environments was, however, a persistent physiological challenge not for the adult amphibians, which could breathe air directly, but for the broader ecosystem in which they existed. Waterlogged soils and stagnant water bodies are characteristically low in dissolved oxygen. Aerobic decomposition of organic matter consumes oxygen rapidly, and in poorly circulated water bodies, this oxygen is not replenished at sufficient rates by diffusion from the atmosphere or by photosynthesis in the water column. The result is hypoxic or anoxic water, water containing little or no dissolved oxygen in which most aerobic aquatic organisms cannot survive. Fish, which depend on dissolved oxygen extracted from water via gill respiration, were therefore not uniformly distributed across all water bodies in these environments. They persisted in flowing systems, rivers and streams, where turbulence maintained oxygen levels, and in lakes with sufficient surface area and wind-driven mixing to prevent stratification. In stagnant backwaters and marsh pools, fish populations were sparse or absent. The predators that occupied these oxygen-depleted environments were those capable of accessing atmospheric oxygen directly, the air-breathing amphibians, and various invertebrate lineages with comparable respiratory adaptations. Some temnospondyle species may have been capable of a form of estivation, a dormancy state comparable to hibernation, in which metabolic rate drops dramatically and the animal remains inactive, often buried in substrate, for extended periods. Modern lungfish exhibit this behavior in response to drought. Whether large Triassic temnospondyls possessed similar capacity is not established with certainty by current fossil evidence, but the physiological logic is consistent with their metabolic profile. An animal with a low metabolic rate and a body plan suited to remaining buried in substrate would, under the right selective pressures, develop behavioral and physiological mechanisms for surviving temporary deterioration of local habitat conditions. Smaller amphibian lineages coexisted alongside the giants in these ecosystems, occupying distinct ecological niches within the same broadly waterlogged landscape. The early lissamphibians, the group that includes the ancestors of modern frogs, salamanders, and caecilians, were present in the Triassic. though their fossil record from this period is fragmentary. These smaller animals occupied the vegetation margins of water bodies, feeding on insects and small invertebrates, and themselves serving as prey for the larger temnospondyls and early archosaurs. Their small body size made them less dependent on large open water bodies and more capable of exploiting the microhabitats created by dense, wet vegetation root tangles, moss mats, flooded leaf litter that the giants could not access. The acoustic environment these animals inhabited was structured in part by their own vocalizations. Modern frogs produce advertisement calls for mate attraction, and the anatomical structures associated with sound production were developing in early amphibian lineages during the Triassic. In an environment dominated by the continuous sound of rainfall, running water, and thunder, acoustic communication would have required either high amplitude, distinctive frequency profiles, or both, to propagate effectively through the ambient noise. The calls of early amphibians in these environments, if they existed, echoed through a world that was already saturated with sound, layered, continuous, and driven by the same water that structured every other aspect of life in the flooded landscape. The relationship between predator body size and prey availability in these ecosystems followed patterns consistent with general ecological principles, but was modulated by the specific conditions of persistent flooding. Large predators require large prey or high prey density to meet their energetic needs. In the flooded Triassic ecosystems, prey diversity was reduced relative to later periods, but prey density in productive water bodies was high. Fish in oxygenated river systems reached substantial sizes during the Triassic. Some ray-finned fish from this period achieved lengths exceeding 1 meter. Smaller tetrapods, both amphibian and reptilian, were present in sufficient numbers across the landscape to sustain predator populations of large amphibians. Competition between large amphibian predators and the emerging archosaurian lineages was real but geographically structured. The archosaurs were not yet ecologically dominant. Their body plans were diverse. Some were heavily armored and low-slung, others more lightly built and capable of a more erect posture, but none had yet achieved the size or ecological impact of the large temnospondyls in fully aquatic or semi-aquatic environments. The flooded lowlands remained, for this interval, fundamentally amphibian territory. That territory was vast. It extended across floodplains and marshes, along river margins and lake shores, and through flooded forest industries, and across open, shallow water bodies covering areas measured in tens of thousands of square kilometers. Within this territory, the giant amphibians moved, waited, fed, and reproduced, large, ancient, and precisely suited to a world defined by water in a geological moment when water was the defining condition of the planet's surface. Across the equatorial and mid-latitude regions of Pangaea, where rainfall was most persistent and drainage most compromised, the land surface supported a plant community unlike any that exists on Earth today. It was not a forest in the conventional sense, a structured community of tall trees with a defined canopy, understory, and ground layer, cycling through seasonal patterns of growth, dormancy, and renewal. It was something closer to a permanent, planet-wide greenhouse, a continuous, humid, densely vegetated expanse in which the boundaries between aquatic and terrestrial environments had largely dissolved, and in which the biological processes governing growth, decomposition, and ecological succession operated under conditions of uninterrupted moisture and reduced solar input. The dominant plant lineages of this environment were not the flowering plants that define most modern forests. Angiosperms, the flowering plants that currently account for the majority of terrestrial plant diversity, had not yet evolved during the Triassic period. The vegetation of Carnian Pangaea was composed of more ancient lineages: ferns and tree ferns, horsetails, lycopsids, early conifers, cycads, and seed ferns, a collective assemblage sometimes referred to as the mesophytic flora, representing the transitional plant communities between the Paleozoic coal swamp forests and the later Mesozoic gymnosperm-dominated landscapes. Each of these groups had different tolerances for waterlogging, different light requirements, and different structural characteristics, and their distribution across the flooded landscape reflected these differences in a spatially complex mosaic of vegetation types. Ferns occupied the lowest and most persistently saturated zones with particular success. Their reproductive strategy, dispersal via lightweight spores rather than seeds, allowed them to colonize newly available surfaces rapidly, including the unstable, frequently disturbed substrates of active floodplains and recently inundated lowlands. Fern spores can remain viable under a wide range of conditions and germinate quickly when moisture and light are available. In an environment where new surfaces were continuously being created by flooding, erosion, and sediment deposition, the capacity for rapid colonization was a significant ecological advantage. Dense fern mats covered the ground surface across broad areas, their fronds forming a low, continuous layer that trapped moisture, slowed surface runoff, and created a microenvironment at ground level characterized by near-saturated humidity and reduced air movement. Above the fern layer, where substrate conditions permitted rooting in slightly better drained soils, tree ferns reached heights of 5 to 10 meters, their fibrous trunks supporting crowns of large, divided fronds that captured the diffuse light filtering through the persistent cloud cover above. These were not fast-growing organisms by modern standards, but in an environment where competition for light was intense and growing conditions were year-round rather than seasonal, vertical growth was a consistently favored strategy. The canopy formed by tree ferns and early conifers was not the closed, high canopy of a modern tropical rainforest. It was lower, more irregular, frequently disrupted by storm damage and the death of individual plants, and continuously reorganizing as gap dynamics played out across the landscape. Horsetails, the genus Equisetum, and its Triassic relatives and predecessors were another dominant element of the wet zone flora. Modern horsetails are modest plants, rarely exceeding 1 to 2 meters in height, and are considered minor components of contemporary wetland vegetation. Their Triassic relatives, however, included forms substantially larger than their modern descendants, and they were ecologically significant components of the flooded margins of water bodies throughout the period. Horsetails are highly tolerant of waterlogged, low-oxygen soils, a tolerance derived from their capacity to transport oxygen internally to their root systems through specialized parenchyma tissue, allowing them to maintain aerobic root metabolism even when the surrounding substrate is anoxic. In the oxygen-depleted soils of the Carnian floodplains, this physiological capability was a critical competitive advantage. The structural consequence of this dominance was a landscape that, viewed from above if such a perspective had been available, would have appeared as an unbroken, multi-textured surface of green and grey-green vegetation interrupted by the dark surfaces of open water. There were no meadows, no grasslands. Grasses would not evolve for another 100 million years, and no broad expanses of bare soil, except where active erosion or very recent flooding had stripped vegetation from the surface. The land was covered. It was covered in plants that had adapted over millions of years of evolutionary history to exactly the conditions that were now most broadly represented across the planet's surface. Within this vegetated matrix, the humidity at ground level was extreme. Transpiration, The process by which plants release water vapor through their leaf surfaces added continuously to the moisture already present from direct precipitation. In a dense plant community with high leaf area index, transpiration rates are substantial. The combined effect of direct rainfall, soil evaporation, and plant transpiration created a boundary layer of air at the surface that was effectively saturated with water vapor at most times. Water condensed on every available surface: leaf undersides, root surfaces, fungal mats, the exoskeletons of invertebrates. Everything that existed at ground level existed in contact with liquid water continuously. This had profound consequences for decomposition dynamics. Fungal decomposers, the primary agents of woody material breakdown in most modern forests, require oxygen for aerobic respiration. In waterlogged conditions, aerobic decomposition slows dramatically. Dead plant material, fallen trunks, shed fronds, root masses accumulated at the surface and in the soil, rather than being rapidly broken down, and its constituent elements return to the available nutrient pool. This accumulation was the process that built peat, and ultimately coal organic matter preserved by the very anaerobic conditions that prevented its decomposition. The forests of Carnian Pangaea were, in the most literal geological sense, building the coal seams that human civilization would extract hundreds of millions of years later. The insect communities inhabiting these forests were diverse and, in several lineages, exceptionally large by modern standards. While the extreme gigantism of Carboniferous insects driven by that period's elevated atmospheric oxygen was not replicated in the Triassic, humidity and vegetation density created conditions favorable to insect proliferation across many groups. Cockroach-like insects, beetles, early flies, and various predatory lineages occupied every layer of the vegetated environment. In the canopy, where some degree of air movement existed and light was marginally better, winged insects exploited the resources offered by reproducing plants, spores, pollen equivalents, and plant tissues. At ground level, and in the leaf litter, detritivorous species processed the accumulating organic matter, forming the energetic base of a complex invertebrate food web. Some predatory invertebrates of the Triassic reached sizes that would be remarkable by modern standards. Certain centipede-like myriapods from this general period achieved lengths exceeding half-a-meter, animals capable of subduing and consuming small vertebrates. In the dense, dark, humid ground layer of the Carnian forests, where visibility was minimal and cover was absolute, such predators would have operated with considerable effectiveness. Their prey, small amphibians, early lizard-like reptiles, large insects, moved through the same environment largely by chemical and tactile sensation rather than vision, navigating a world in which sight was of limited utility and other sensory modalities had been favored by selection. The canopy of these forests, irregular and frequently disrupted as it was, performed a significant role in the broader hydrological cycle of the region. Rainfall intercepted by vegetation does not reach the ground immediately. It is held temporarily on leaf surfaces, evaporates back into the atmosphere, drips from leaf margins in concentrated flows, or runs down stems and trunks to reach the soil at specific points. This interception modifies the effective intensity of rainfall at the ground surface, breaking the kinetic energy of large raindrops that would otherwise compact and seal soil surfaces, and distributing the arrival of water more gradually through the system. In forests with high canopy cover, a significant fraction of total rainfall in modern tropical forests, estimates range from 10 to 40%, never reaches the ground directly, being evaporated from leaf surfaces before it can run off. The Carnian forests were therefore not simply passive recipients of atmospheric water, They were active participants in the hydrological system, cycling water between the soil, the vegetation, and the atmosphere in a continuous loop that modified local rainfall patterns, maintained surface humidity, and regulated the rate at which water moved through the landscape. Remove the vegetation, and rainfall intensity at the ground surface would have increased, runoff would have accelerated, and erosion would have been more severe. The forests stabilized the very conditions that were, simultaneously, challenging their existence. This interdependence between the water that the atmosphere delivered and the vegetation that modulated its effects was a defining characteristic of the Carnian terrestrial system. The forests existed because the rain fell. The rain, in part, fell where it did because the forests were there to maintain the humidity and thermal conditions that supported continued precipitation. Neither element was independent of the other. They were components of a single, coupled system operating across millions of square kilometers of Pangaean surface, sustained by the same atmospheric engine that had set the entire wet phase in motion, and that showed, across the Middle Triassic, no indication of diminishing. The dinosaurs did not arrive into an empty world. They emerged gradually, ambiguously, without any threshold moment that the fossil record marks with precision into ecosystems that were already occupied, already structured, and already under significant environmental stress. The landscape into which the earliest dinosaur lineages diversified was the same waterlogged, storm-dominated, amphibian-ruled terrain that had been accumulating ecological complexity for millions of years. The first dinosaurs were not conquerors of a vacant stage. They were latecomers to a crowded and difficult environment, and their early history is inseparable from the conditions of persistent rainfall and ecological instability that defined the Carnian world. The earliest unambiguous dinosaur fossils are recovered from formations dating to approximately 230 to 233 million years ago, placing their origin squarely within or immediately adjacent to the Carnian pluvial episode. The Ischigualasto Formation of northwestern Argentina, deposited in a fluvial and lacustrine environment during this interval, has yielded some of the oldest known dinosaur material, including Eoraptor lunensis and Herrerasaurus ischigualastensis. These were not large animals by later dinosaur standards. Eoraptor was a small, lightly built biped estimated at approximately 1 meter in length and 1 kilogram or less in mass. Herrerasaurus was larger, reaching perhaps 3 to 4 meters in length, but was still a minor ecological presence relative to the dominant predators of its time. The environment recorded by the Ischigualasto Formation was not uniformly wet. Sedimentological analysis of the formation indicates a seasonally variable climate intervals of high rainfall alternating with drier periods, producing a mosaic of fluvial channels, floodplain deposits, and paleosols reflecting intermittent drying. This variability is itself significant. The Carnian wet phase was not geographically uniform. It was most intense in certain regions, particularly those with direct atmospheric connection to the warm Tethys Ocean, and modulated by local topography, continental position, and the complex internal dynamics of the Pangaean atmospheric system. In higher latitude or more interior regions, the wet phase expressed itself as increased seasonal rainfall rather than year-round inundation. The early dinosaur record comes, in part, from exactly these transitional zones, environments that were wetter than the preceding Anisian and Ladinian stages, but not so completely waterlogged as the most extreme lowland regions. This geographic positioning may not be coincidental. The transitional zones between persistently flooded lowlands and more seasonally variable uplands represented a specific ecological context, one in which neither the large amphibians fully optimized for permanent water nor the more drought-tolerant archosaurs of the drier interior held absolute competitive dominance. In these intermediate environments, ecological opportunity existed for lineages capable of tolerating both wet and intermittently dry conditions. The earliest dinosaurs, based on available evidence, were precisely such generalists, small, bipedal, metabolically capable of activity across a range of environmental conditions, and not tightly constrained to either fully aquatic or fully arid habitats. The locomotor anatomy of early dinosaurs is directly relevant to their ecological success in variable, unstable environments. The evolution of an erect parasagittal limb posture in which the limbs are positioned directly beneath the body rather than sprawling laterally is one of the defining characteristics of the dinosaurian lineage. This posture, which dinosaurs share with modern birds and mammals, but not with most other reptilian groups, has significant functional consequences. It allows more efficient locomotion at sustained speeds, reduces the energetic cost of breathing during movement because the lungs are not compressed by the lateral undulation of the body as they are in sprawling animals, and permits more precise foot placement on irregular, unstable substrate. In a landscape characterized by saturated, uneven ground, fallen vegetation, shallow water of variable depth, and frequent obstacles created by flood debris, the ability to place the feet precisely and move efficiently over irregular terrain was a meaningful advantage. The sprawling gait of large temnospondyls was well suited to flat, shallow water, but less efficient on complex terrestrial substrate. Early archosaurs with more erect postures had already demonstrated the locomotor advantages of this body plan. The early dinosaurs, with a fully developed erect posture and lightweight bipedal body plan, extended this advantage further. The dietary ecology of the earliest dinosaurs was diverse across lineages, reflecting the ecological opportunism that characterized these small, adaptable animals. Herrerasaurus was a carnivore. Its dentition, featuring recurved, laterally compressed teeth with serrated edges, is consistent with a diet of other vertebrates. It was likely preying on the small reptiles, early mammals, and possibly juvenile amphibians that shared its fluvial environment. Eoraptor, despite initially being classified as a carnivore, shows dental characteristics suggesting omnivory. Some teeth are leaf-shaped and consistent with plant processing, while others are more blade-like and suited to animal prey. This dietary flexibility would have been advantageous in an environment where resource availability fluctuated with rainfall patterns and seasonal flooding. Other early dinosaur-adjacent lineages, the Silsaurids, which represent either early dinosaurs or the closest non-dinosaurian relatives of dinosaurs, depending on the phylogenetic analysis, consulted appear to have been predominantly herbivorous, feeding on the ferns, seed ferns, and low vegetation that formed the ground layer of Triassic plant communities. In the flooded lowlands, this vegetation was abundant but nutritionally variable. Ferns, in particular, contain high concentrations of structural carbohydrates that are energetically expensive to digest and relatively low in protein. Herbivores in these environments required either specialized digestive systems capable of processing large volumes of low-quality plant material, or selective feeding strategies targeting the most nutritious available plant tissues. Competition between early dinosaurs and the established fauna of the Carnian was real and, based on the fossil record, not immediately resolved in the dinosaurs' favor. For a significant portion of the Carnian and into the Norian stage that followed, dinosaurs remained a minor component of terrestrial vertebrate faunas. The dominant large-bodied predators were attosaurs, heavily armored, pig-like herbivorous archosaurs, and rauisuchians, large-bodied carnivorous archosaurs that occupied the apex predator role across much of Pangaea during the mid to late Triassic. These animals were not displaced by the arrival of dinosaurs. They coexisted with the early dinosaur lineages for millions of years, maintaining ecological dominance in most environments. The conditions created by persistent rainfall during the Carnian may have contributed to this delayed dinosaurian rise by maintaining the ecological stability, however stressed, of the existing fauna. The large amphibians and established archosaurian groups were adapted to the wet conditions. They were reproducing successfully, occupying the available ecological roles, and not easily displaced by small, generalist newcomers. Ecological displacement of established fauna by new lineages typically requires either a significant competitive advantage in the new lineage, a major environmental disruption that removes the incumbents, or both. During the peak of the Carnian wet phase, the environmental conditions favored the incumbents. The evolutionary pressures acting on early dinosaur populations during this interval were, however, continuously shaping the lineage in ways that would have consequences far beyond the Carnian. Small body size and bipedal locomotion, maintained by selection in the variable environment conditions of the transitional zones, were associated with specific physiological characteristics, including evidence from bone histology of early dinosaurs of relatively rapid growth rates compared to other reptilian contemporaries. Rapid growth is associated with elevated metabolic rates, and elevated metabolic rates are associated with greater thermal independence from the environment, a characteristic that would confer significant advantages in the variable, often cloudy, thermally inconsistent conditions of the Carnian landscape. Whether early dinosaurs were fully endothermic, capable of maintaining a stable internal body temperature through metabolic heat production, as modern birds and mammals do, is a question that paleontological evidence has not definitively resolved. Current interpretations of bone microstructure, growth rates, and isotopic data from Triassic dinosaur material suggest that early dinosaurs occupied a metabolic position intermediate between the ectothermy of most modern reptiles and the full endothermy of modern birds. This intermediate physiology, sometimes described as mesothermy, would have allowed early dinosaurs to remain active across a broader range of ambient temperatures than fully ectothermic competitors, while not incurring the full energetic cost of continuous endothermic heat production. In the flooded, cloud-covered environments of Carnian Pangaea, where solar radiation at the surface was reduced and ambient temperatures fluctuated with storm activity and cloud cover, the ability to maintain activity independent of external heat sources was significant. A temnospondyle lying in shallow water on an overcast day unable to bask, body temperature dropping toward ambient water temperature, would have experienced a reduction in muscular performance and reaction speed. An early dinosaur with a higher intrinsic metabolic rate would have retained more of its locomotor and sensory capacity under the same conditions. These advantages were modest in absolute terms during the Carnian itself. They did not immediately translate into ecological dominance, but they were being selected for, generation after generation, in populations of small bipedal archosaurs navigating a world that was simultaneously hostile and full of unexploited opportunity. The rain that fell on these early dinosaurs was the same rain that was drowning the ecosystems around them, driving the evolution of every lineage that survived it, and slowly across timescales, no individual animal could perceive building the selective pressures that would eventually produce one of the most ecologically successful vertebrate radiations in the history of life. Earth. Sustained environmental pressure, applied consistently across thousands of generations, does not merely eliminate the unfit, it sculpts the survivors. The organisms that persisted through the prolonged wet phase of the Carnian were not simply those that happened to tolerate moisture, they were lineages, actively shaped at the level of morphology, physiology, and behavior by the specific and unrelenting demands of a world in which water was the dominant environmental variable. The adaptations that emerged from this selective pressure were not random variations that happened to prove useful. They were the accumulated outcomes of differential survival across timescales long enough to reorganize entire body plans, redirect developmental pathways, and establish ecological relationships that had no precedent in the drier world that had preceded them. The most immediately visible category of adaptation was integumentary, the outer covering of the body, which in any terrestrial or semi-aquatic animal mediates the critical interface between the organism and its environment. For amphibian lineages, the skin was both an asset and a constraint. Amphibian skin is highly permeable to water and gases, allowing cutaneous respiration, the exchange of oxygen and carbon dioxide directly through the skin surface, which supplements pulmonary breathing in many species. In a humid environment, this permeability was advantageous. The skin remained moist without active effort, gas exchange occurred continuously, and the animal was effectively using its entire body surface as a supplementary respiratory organ. Larger amphibians, with their lower surface area to volume ratios, were more dependent on pulmonary respiration, but the cutaneous contribution remained physiologically meaningful. For the reptilian lineages sharing these environments, including the early archosaurs and their relatives, the integumentary situation was structurally different. Reptilian scales are composed of beta-carotene, a protein that forms a relatively impermeable barrier to water loss. This impermeability was the defining physiological characteristic that had originally allowed reptiles to colonize drier environments during the Permian when amphibians were constrained to remain near water. In the persistently wet conditions of the Carnian, this advantage was reversed in one specific sense. A waterproof skin that resisted desiccation was less immediately necessary when the environment provided continuous moisture. But it retained a different kind of value. It protected the animal from the consequences of excessive water absorption in hypertonic environments, where osmotic gradients could otherwise draw water into the body across a permeable membrane. Early reptiles in flooded environments therefore occupied a physiologically distinct position from their amphibian contemporaries. They could move between wet and dry microhabitats, where these existed without the immediate risk of desiccation that constrained amphibian movement. They could enter bodies of fresh water without risk of osmotic swelling. Their skin, scaled and relatively impermeable, was a stable interface that functioned effectively across a range of moisture conditions. In a landscape where moisture conditions varied across short distances, from standing water to saturated soil to relatively drier, elevated ground, this versatility was a persistent advantage. Respiratory adaptations in the larger animals of these ecosystems reflected the oxygen dynamics of their environment. The wetlands and stagnant water bodies of Carnian Pangaea were, as previously established, frequently hypoxic. Animals that relied on dissolved oxygen extracted from water via gill respiration were constrained to oxygenated water bodies. Animals capable of extracting oxygen from air directly were not subject to this constraint and could exploit the full range of water body types available in the landscape, including the stagnant, organically rich pools that supported high prey densities precisely because of their chemical hostility to gill-breathing competitors. Lung morphology in both amphibian and early reptilian lineages of the Triassic showed characteristics consistent with environments where aerial oxygen availability was not always optimal. Elevated carbon dioxide concentrations in air near stagnant water produced by the respiration and decomposition activity of microbial communities processing organic matter would have required animals breathing this air to maintain higher ventilation rates to achieve adequate gas exchange. Selection for larger lung capacity and more efficient ventilation mechanics is a predictable response to this pressure. Bone histological evidence and body cavity reconstructions from Triassic tetrapod fossils suggest that thoracic volume, and by implication, lung capacity relative to body size, was well developed in many lineages of this period. Camouflage, as an adaptive strategy, is difficult to recover directly from the fossil record. Coloration and patterning are not preserved in bone or sediment under most conditions. However, the functional logic of camouflage in the Carnian environment is sufficiently clear that its presence in the fauna can be reasonably inferred from ecological first principles. An environment characterized by dark water, green-brown vegetation, mud, and organic debris provides a specific visual background against which certain colorations and patterns would confer concealment, while others would not. Animals that were cryptic against this background, whether through countershading, disruptive patterning, or simple coloration matching the substrate, would have experienced lower predation rates, and this differential survival would have been sufficient to drive the evolution of cryptic coloration over generations. Modern amphibians show extraordinary diversity of camouflage strategies, from the leaf litter mimicry of certain frog species to the bark-matching coloration of tree frogs. Modern crocodilians, whose lineage extends back into the Triassic, are cryptically colored in gray, brown, and olive tones that render them nearly invisible in the turbid, vegetated water margins they inhabit. The selective pressures that produce these modern camouflage strategies were operating in analogous form in the Carnian ecosystems. Predators that were indistinguishable from their background caught more prey. Prey animals that were indistinguishable from their background were caught less often. Both selective vectors operated simultaneously, producing a landscape populated by animals that were, in aggregate, visually integrated into their environment to a degree that would have made detecting individual organisms extremely difficult. Parasitic organisms thrived in the humid conditions of the Carnian wetlands with particular intensity. Parasitism as an ecological strategy is favored by high host density, close physical proximity between hosts, and environmental conditions that support the survival and transmission of parasite life stages. The flooded ecosystems of the Carnian provided all of these conditions simultaneously. Host animals, both vertebrates and invertebrates, were abundant and often concentrated in the most productive water bodies. Physical contact between individuals was frequent in shallow water environments where movement was constrained. The warm, humid conditions maintained at the surface were optimal for the survival of parasite eggs, larvae, and intermediate life stages that required external environmental exposure during their transmission phase. Ectoparasites, those living on the external surface of the host, would have included early mite and tick lineages whose origins extend into the Paleozoic and which were certainly present in Triassic ecosystems. The dense, humid vegetation of the Carnian forests provided ideal microhabitats for questing ectoparasites waiting for a host to pass within attachment range. Endoparasites, internal worms, protozoans, and early representatives of various parasitic lineages would have transmitted through the water and food that host animals consumed, through skin penetration in the case of certain larval stages, and through intermediate hosts such as fish and invertebrates that were themselves consumed by larger vertebrates. The immunological demands placed on host organisms by high parasite loads are substantial. Maintaining an effective immune response requires energetic investment. Resources allocated to immune function are resources not available for growth, reproduction, or activity. In an environment where food resources were sometimes abundant and sometimes constrained by flooding-driven ecological disruption, the energetic cost of parasite defense was a meaningful component of each animal's overall energy budget. Lineages that evolved more effective immune responses or behavioral strategies that reduced parasite exposure, such as avoiding stagnant water in favor of flowing systems, or grooming behaviors that removed ectoparasites, would have experienced selective advantages over those that did not. Behavioral adaptations to the conditions of endless rain extended beyond parasite avoidance. The timing of activity, the dial pattern of when an animal is active versus resting, is a behavioral trait with strong environmental determinants. In modern ecosystems, many predators are crepuscular or nocturnal, timing their activity to periods of lower light when their prey is less able to detect them visually. In the dim, overcast conditions of Carnian Pangaea, the distinction between day and night in terms of available light was less extreme than in a modern environment with clear skies. Cloud cover attenuated daylight to levels that, in the densest parts of the flooded forests, may have been comparable to modern twilight conditions even at midday. This reduction in the day-night light differential would have altered the selective advantage of strictly nocturnal versus diurnal activity patterns. Animals previously constrained to nighttime activity by the detection risk associated with bright daylight could have expanded their activity into daytime hours under persistent overcast conditions. Conversely, animals that depended on daylight for visual hunting would have found the dim, cloud-filtered illumination of Carnian days less effective than in a world with regular clear skies. Selection would have favored sensory systems less dependent on high-intensity light, larger eyes with more rod photoreceptors for low-light sensitivity, enhanced olfactory capabilities, lateral line analogues in semi-aquatic forms capable of detecting water movement, and tactile sensitivity in the limbs and facial regions. The cumulative result of these intersecting selective pressures, integumentary, respiratory, camouflage, immunological, behavioral, and sensory, was a fauna that was, by the middle of the Carnian, deeply and specifically adapted to its environment. These were not generalist organisms tolerating conditions outside their evolutionary experience. They were organisms whose entire biological architecture had been shaped by the rain, by the darkness it created, by the water it deposited, by the parasites it supported, by the prey it concentrated, and by the predators it concealed. Every aspect of their morphology and behavior encoded, in some form, the history of the selection pressures that the endless storm had imposed on every generation that had lived and died within it. That specificity was both their strength and, in the longer view of geological time, their vulnerability. Organisms exquisitely adapted to a specific set of environmental conditions are, by definition, less prepared for conditions that differ substantially from those that shaped them. The rain that had built these creatures, generation by generation, into precisely the forms they had become, would not fall forever. And the world that would eventually replace it would belong to those whose adaptations, by chance or by the broader logic of evolutionary contingency, translated more effectively into the drier, more variable, and ultimately more competitive environments that lay ahead. Pangaea, at the height of the Carnian wet phase, was a landmass of continental proportions experiencing environmental conditions that differed fundamentally across its vast interior. The supercontinent stretched from polar latitudes in the south to polar latitudes in the north, spanning more than 250 degrees of longitude at its widest extent and encompassing terrain ranging from active mountain belts along its margins to broad, flat interior basins thousands of kilometers from any coastline. The wet phase did not act uniformly across this entire surface. It was modulated by distance from moisture sources, by topographic barriers, by the position of the intertropical convergence zone, and by regional volcanic activity that contributed both heat and atmospheric particulates to local climate systems. But in the equatorial lowlands, the broad, flat, internally drained basins that occupied much of Pangaea's tropical interior, the accumulated effects of persistent rainfall produced environments of a specific and extreme character. The great black swamps that would leave their chemical signature in the geological record for hundreds of millions of years. The term black, applied to these environments, is not metaphorical. It describes, with reasonable precision, the actual optical character of the water bodies that dominated the landscape. Water in heavily vegetated wetland systems acquires color from dissolved organic compounds, primarily humic and fulvic acids, produced by the partial decomposition of plant material under anaerobic conditions. These compounds, collectively referred to as dissolved organic carbon, absorb light across the visible spectrum with particular efficiency at shorter wavelengths, giving the water a dark brown to black appearance. Modern blackwater rivers, the Rio Negro in Amazonia, is the most extensively studied example to achieve this coloration through identical processes operating in comparable ecological contexts. The blackwater swamps of Carnian Pangaea were produced by the same chemistry, operating at a far greater spatial scale and over a far longer continuous duration. The ecological consequences of blackwater conditions extend well beyond visual appearance. Humic acids are mildly acidic, and their accumulation in standing water bodies reduces pH to levels that suppress the activity of many decomposer organisms, further slowing the breakdown of organic material and reinforcing the accumulation of dissolved organic carbon in a self-perpetuating chemical cycle. Low pH also reduces the availability of certain nutrients, particularly phosphorus, which precipitates out of solution at low pH, creating oligotrophic conditions in which primary productivity is limited despite the abundance of water. The blackwater swamps were, paradoxically, biologically rich in some respects and nutrient-poor in others. High in organic carbon, but low in the mineral nutrients that support dense phytoplankton growth or lush aquatic plant communities. This nutrient profile shaped the food web architecture of these water bodies in specific ways. Allochthonous inputs, organic material produced outside the water body and transported into it, primarily as plant debris from the surrounding terrestrial vegetation, were the dominant energy source supporting aquatic food webs rather than in situ primary production. Invertebrates specialized for processing coarse and fine particulate organic matter shredders, collectors, and filterers in the functional feeding group, terminology of modern stream ecology, were the energetic foundation of the system. These invertebrates supported small fish and amphibian larvae where oxygen levels permitted, and the entire aquatic food chain ultimately traced its energy to the decomposing plant material continuously entering the water from the surrounding flooded forest. Volcanic activity contributed to the environmental character of the Carnian interior in ways that extended beyond their role in atmospheric carbon dioxide loading. Pangaea in the Triassic period was not volcanically inactive. The breakup of the supercontinent, which would begin in earnest during the Jurassic, was preceded by extensional tectonics, the stretching and thinning of the continental crust along zones of incipient rifting that produced significant volcanic activity along developing rift systems. The Central Atlantic Magmatic Province, one of the largest large igneous provinces in the geological record, was beginning to form during the late Triassic, with its most intense activity concentrated somewhat later than the Carnian peak. However, regional volcanism associated with early rifting was active during the Carnian interval, contributing basaltic material, volcanic ash, and thermally driven convective activity to the atmospheric and surface systems of the interior. Volcanic heat flux from active regions warmed the lower atmosphere locally, intensifying convective storm development over and downwind of volcanic centers. Volcanic ash deposited on water surfaces and vegetation temporarily altered the reflectivity and chemistry of the surfaces it covered, suppressing some biological activity, releasing soluble minerals that could briefly alter nutrient availability, and contributing fine particulate material to the aerosol loading of the lower atmosphere. In an atmosphere already carrying high moisture loads, additional aerosol particles provided more condensation nuclei, the microscopic surfaces around which water vapor condenses to form cloud droplets, potentially enhancing cloud formation and precipitation efficiency in volcanic downwind regions. The rivers that drained these volcanic interiors and transported their weathering products toward the continental margins were not clear, high-gradient systems. They were low-gradient, meandering or anastomosing channels moving slowly across nearly flat terrain, carrying high loads of fine suspended sediment and dissolved organic material. Channel geometry in low-gradient fluvial systems is controlled by the balance between water discharge, sediment supply, and bank resistance. In the Carnian interior basins, bank resistance was low. The saturated, organic-rich soils that formed the channel margins offered little resistance to erosion, and sediment supply was high. Rivers migrated laterally across their floodplains, constantly reworking the sediment they had previously deposited, creating a braided, anastomosing network of channels separated by low, vegetated islands of uncertain permanence. Dead vegetation accumulated in these channels in enormous quantities. Fallen trees, transported from upstream by floodwaters, became waterlogged and sank to the channel bed or accumulated in logjams at points of reduced flow velocity. Logjams in high-discharge river systems are not minor obstructions. They are hydraulically significant structures that redirect flow, cause local scour and deposition, raise water levels upstream, and create extensive areas of backwater habitat behind them. In the Carnian rivers, where woody debris was continuously supplied by the death of floodplain trees and the erosion of vegetated banks, logjam formation was likely a persistent and widespread feature of channel morphology, creating complex, heterogeneous aquatic habitats within what might otherwise have been relatively uniform channel environments. The fauna of these river systems and their associated floodplains was structured by the physical complexity of the environment. Predators in river channels occupied positions near hydraulic discontinuities, the edges of logjams, the downstream end of channel bends where velocity dropped and sediment accumulated, the shallow margins where water depth transitioned from navigable to impassable. These positions offered concealment, proximity to areas of high prey activity, and the hydraulic advantage of being positioned where prey animals moving downstream were funneled by channel geometry into predictable paths. Large temnospondylus in river environments were capable of exploiting this spatial structure effectively. Their flattened body profiles and ability to remain motionless for extended periods made them difficult to distinguish from submerged logs, an accidental but functionally effective mimicry that would have deceived prey animals at close range. The logjam environments of Carnian rivers were therefore doubly dangerous for smaller animals. Structurally complex enough to make navigation difficult and unpredictable, and occupied by large predators whose concealment was enhanced by the very debris that created the complexity. Smaller predators, early archosaurs, juvenile temnospondyls, large predatory insects occupied the interstices of these environments, exploiting prey resources that the largest predators could not efficiently access. The spatial heterogeneity of the logjam-influenced river system created a three-dimensional ecological structure with distinct microhabitats at scales of centimeters to meters, each supporting different combinations of species and functional groups. This heterogeneity maintained biodiversity within what might, at a coarser scale, appear to be a monotonous and uniformly wet landscape. The darkness that characterized the interior of the flooded forests extended, in modified form, into the open water bodies of the swamp systems. In blackwater environments, light penetration is severely limited. In modern blackwater rivers, the photic zone, the depth to which sufficient light penetrates for photosynthesis, is often less than 1 meter. Below this depth, the water column is in permanent darkness. Animals living and moving in this darkness relied on non-visual sensory systems, chemoreception to detect dissolved substances indicating the presence of prey, predators, or conspecifics, mechanoreception to detect pressure waves and water movements, and in some lineages, electroreception, the detection of weak electric fields generated by the muscular activity of other animals, a sensory modality present in several modern groups of freshwater fish whose origins extend into the Paleozoic. The acoustic environment of the black swamps was layered and continuous. Rain on open water surfaces produced broadband noise, a white noise background against which biological signals had to be distinguished. Thunder generated low-frequency pressure pulses that propagated through both air and water, potentially detectable by mechanoreceptive systems in aquatic animals. The calls of amphibians, if present, competed with this background across whatever frequency ranges their vocal anatomy produced. Fish in these environments communicated through pressure wave generation movements and vibrations that propagated through the water column and were detectable by the lateral line systems present in all fish lineages. The claustrophobic character of these environments, a term that carries anthropomorphic implications but describes a real spatial reality derived from the combination of limited visibility, dense physical structure, and acoustic complexity that characterized the flooded interior basins of Carnian Pangaea. Movement through these environments by any animal larger than a few centimeters required constant navigation of physical obstacles. Submerged root masses, floating debris, shallow substrate that shifted underfoot, channels of uncertain depth concealed beneath a uniform water surface. Every movement carried the risk of encounter with a predator that was indistinguishable from its background. Positioned at a hydraulic advantage and capable of reacting faster than any prey animal could process the sensory information indicating its presence. The black swamps were not simply wet, they were environments of compressed space, reduced information, and concentrated biological interaction ecosystems in which the physical conditions of the Carnian wet phase had been distilled to their most extreme expression. They persisted across millions of years, building the chemical and sedimentary record that geologists would eventually read as evidence of one of Earth's most unusual climatic intervals, layer by layer in the dark. Extinction is not always a sudden event. The geological record preserves several examples of rapid, catastrophic biodiversity loss: the end Permian event, the end Cretaceous impact, in which species disappearance is concentrated within intervals so brief, by geological standards, that the boundary between a world with those species and a world without them is detectable as a thin layer in the rock. But extinction also operates through slower mechanisms. The gradual contraction of viable habitat, the progressive failure of reproductive success, the incremental tipping of competitive relationships until populations that were once stable become too small and too fragmented to recover from ordinary environmental variability. The biological consequences of the Carnian pluvial episode on the fauna and flora of Pangaea represent this second mode, not the sharp, catastrophic boundary of an impact or a volcanic winter, but the slow, grinding attrition of lineages whose ecological requirements were incompatible with a world that was becoming, degree by degree and flood season by flood season, increasingly hostile to them. The extinction signal associated with the Carnian pluvial episode is recorded in multiple fossil assemblages across different continents and different taxonomic groups. In marine environments, the Carnian is associated with a significant turnover in reef-building communities. Sponge and coral assemblages that had been rebuilding after the end Permian extinction experienced renewed disruption during the wet phase, as increased continental runoff delivered elevated loads of fine sediment and dissolved organic material to shallow marine environments. Reef-building organisms are sensitive to water clarity. The symbiotic photosynthetic algae that provide much of the energy supporting coral and sponge growth require light penetration to function, and the turbidity plumes, generated by Carnian continental erosion, extended into coastal marine environments, reducing light availability in shallow water ecosystems that had previously been sufficiently clear to support carbonate reef development. On land, the extinction signal is more complex to read, partly because terrestrial fossil preservation is inherently patchier than marine preservation, and partly because the Carnian fauna was already in a state of elevated ecological flux following the end Permian recovery. Distinguishing Carnian extinction events from the background turnover of a still recovering post-Permian biosphere requires careful stratigraphic analysis and comparison across multiple geographic regions. Nevertheless, several patterns emerge from the available fossil record that are consistent with environmental stress specifically associated with the wet phase. Among the plant communities, the Carnian is marked in several regional sequences by a distinct vegetational turnover event, sometimes referred to as the Carnian crisis in botanical literature, in which the seed fern-dominated floras of the preceding Ladinian stage were progressively replaced by conifer-dominated floras better adapted to the specific conditions of the wet phase. This replacement was not instantaneous. It unfolded across stratigraphic intervals representing tens of thousands to hundreds of thousands of years, reflecting the generational timescales over which plant community composition changes in response to sustained environmental shifts. The seed ferns, an informal grouping of pteridosperms that had been ecologically significant components of Permian and early Triassic plant communities, declined substantially across this interval. Their decline was not a random event. It reflected the specific incompatibility between their reproductive strategies and the persistently waterlogged, frequently disturbed conditions of the Carnian landscape. Animal communities on land experienced analogous pressures. The Dicynodont, Therapsids, large, herbivorous, mammal-like reptiles that had been among the most abundant large herbivores in the early Triassic, declined significantly during the Carnian interval in many regions. Dicynodonts had survived the end Permian extinction in substantial diversity and had been ecologically dominant across broad areas of Pangaea during the early and middle Triassic. Their decline during the Carnian is recorded in faunal assemblages from multiple continents, where their remains become progressively less common in stratigraphic sections spanning the wet phase. The mechanism of their decline is not definitively established, but the pattern is consistent with habitat loss, specifically the reduction of the relatively dry, open vegetation communities that many Dicynodont lineages appear to have preferentially occupied, as these were progressively replaced by the dense, waterlogged vegetation of the expanding wet zone. The Rhynchosaurs, a group of beaked, herbivorous archosaurs that were abundant in Middle Triassic faunas across much of Pangaea, show a similar pattern of decline during the Carnian. Rhynchosaurs were specialized herbivores, with dental and jaw anatomy adapted for processing specific types of seed fern vegetation. As the seed fern communities they depended upon contracted during the Carnian vegetational turnover, Rhynchosaur populations contracted with them. This is a classic case of specialist extinction driven by the loss of a keystone resource, a pattern recognizable in modern conservation biology and clearly operating in the Carnian ecosystem as well. When the plants that a specialized herbivore depends upon decline, the herbivore declines in direct proportion. Disease propagation in the persistently wet, warm conditions of the Carnian swamps was a stressor whose magnitude is difficult to quantify from the fossil record, but whose general significance is inferable from ecological first principles. Pathogens, bacteria, fungi, protozoa, and viruses are transmitted more effectively under conditions of high humidity, elevated temperature, and close physical proximity between hosts. All three of these conditions were met persistently and simultaneously in the flooded ecosystems of Carnian Pangaea. Waterborne pathogens, in particular, would have proliferated in the stagnant, organically rich water bodies that covered enormous areas of the continental surface. Modern wildlife disease ecology demonstrates that high host density combined with environmental conditions favorable to pathogen survival produces disease dynamics fundamentally different from those operating in lower density, more variable environments. Epidemic transmission events in which a pathogen spreads rapidly through a dense, immunologically naive population are more likely, more severe, and more difficult for affected populations to recover from when environmental conditions continuously favor pathogen persistence. In the Carnian wetlands, where animal populations were concentrated in the most productive water bodies and where the water itself served as a transmission medium for waterborne pathogens, epidemic events among aquatic and semi-aquatic vertebrates were likely a recurring feature of the biological landscape. Starvation operated as an extinction mechanism through several pathways that were specific to the conditions of chronic flooding. Plants whose root systems drowned in persistently waterlogged soils died, reducing the total primary productivity of terrestrial ecosystems in affected regions. Herbivores, dependent on terrestrial vegetation, experienced reduced food availability as plant communities were replaced by those tolerant of waterlogging, often species with lower nutritional value, higher structural carbohydrate content, or chemical defenses against herbivory. As herbivore populations declined, the predators dependent on them as prey also experienced reduced food availability, triggering cascading effects through multiple trophic levels. In aquatic environments, the opposite problem sometimes manifested. Stagnant, poorly oxygenated water bodies could support dense microbial communities but sparse populations of aerobic organisms. Fish and amphibian larvae in these environments faced competition for limited dissolved oxygen, suppressed growth rates, and elevated mortality. Mass mortality events in seasonally varying water bodies, where oxygen depletion during warmer periods pushed dissolved oxygen concentrations below the survival threshold for gill-breathing organisms would have produced localized extinction pulses affecting the aquatic components of regional food webs. Fossil bone beds from Triassic formations in several regions record exactly these localized mortality events. Concentrations of skeletal material from multiple individuals of the same or related species deposited rapidly in fine-grained sediment consistent with a low-energy aquatic environment are interpreted as mass death. Assemblages groups of animals that died simultaneously or over a short interval in response to a common environmental stressor. Oxygen depletion, toxic algal blooms, and rapid water body contraction during brief drier intervals within the overall wet phase are all mechanisms consistent with the preservation patterns observed in these assemblages. The cumulative demographic effect of these intersecting stresses, habitat loss, dietary resource contraction, disease, starvation, and localized mortality events was population decline across multiple lineages simultaneously. Population decline, if sustained across sufficient time, crosses thresholds below which recovery becomes probabilistically unlikely. Small populations are vulnerable to stochastic extinction, random variation in birth and death rates. In large populations, averages out, but in small populations can produce extinction through chance alone. They are also vulnerable to inbreeding depression, in which the loss of genetic diversity in isolated, shrinking populations reduces fitness and adaptive capacity. And they are vulnerable to ALI effects, the reduction in reproductive success that occurs at low population density when mate finding becomes difficult. Cooperative behaviors requiring group size are no longer possible, or predation rates increase disproportionately as protective group behaviors break down. The Carnian pluvial episode did not produce a single, geologically instantaneous mass extinction comparable to the end Permian or end Cretaceous events. What it produced was a prolonged interval of elevated extinction rates, a biotic crisis unfolding across hundreds of thousands to millions of years, eroding the diversity and abundance of multiple lineages simultaneously through mechanisms that were individually familiar but collectively overwhelming in their combined effect. The world that emerged from the far side of this crisis was biologically different from the world that had entered it, not because a single catastrophic event had reset the ecological slate, but because the slow, relentless pressure of water applied across geological time had selectively eliminated those lineages least capable of enduring it. The fossil record encodes this transition in sediment and bone, in the changing assemblages of species preserved across stratigraphic sections spanning the Carnian interval, in the chemical signatures of waterlogged soil preserved as paleosols, in the isotopic records of carbon and oxygen that track the changing composition of the atmosphere and ocean during the wet phase. Reading this record requires the integration of evidence from multiple disciplines: paleontology, sedimentology, geochemistry, and paleoclimatology, and the result is not a simple narrative of cause and effect, but a complex, probabilistic reconstruction of a biotic crisis that had no single cause and no single moment of resolution. What it left behind, in the lineages that survived, was the biological foundation of the Mesozoic world, a fauna and flora selected, filtered, and shaped by the demands of an environment that no longer existed by the time the selection was complete. The survivors carried within their physiology and their ecological relationships the imprint of the rain that had killed so much around them, and that imprint would persist, encoded in evolutionary history, long after the last clouds of the Carnian wet phase had finally cleared. Evolution does not operate in isolation from the physical world, it is driven by it. The selective pressures that determine which individuals survive to reproduce and which do not are embedded in the specific environmental conditions of the time and place in which a population exists. Change the environment substantially and persistently, and the direction of selection changes with it. Maintain that changed environment across millions of years, across hundreds of thousands of generations for short-lived organisms, across tens of thousands for larger ones. And the cumulative effect of altered selection is not marginal adjustment, but fundamental biological transformation. The Carnian pluvial episode represented exactly this kind of sustained directional environmental forcing, and its consequences for the trajectory of vertebrate evolution on land were not incidental. They were structural changes to the basic architecture of the biosphere that persisted long after the rainfall itself had ceased. The most significant evolutionary consequence of the wet phase was not the extinction of particular lineages, though those extinctions were real and consequential. It was the differential survival and subsequent radiation of lineages whose pre-existing characteristics happened to confer resilience under the specific conditions that the Carnian imposed. This phenomenon, in which a pre-existing trait evolved originally in a different context, proves advantageous under new environmental conditions and enables rapid diversification when those conditions arise, is sometimes described in evolutionary biology as exaptation. The traits that allowed certain lineages to survive the Carnian were not, in most cases, traits that had evolved specifically in response to the wet phase. They were traits with earlier origins that the wet phase revealed to be advantageous in ways their original selective context had not anticipated. The erect locomotor posture of early dinosaurs and their closest relatives is the clearest example of this principle operating during the Carnian interval. Erect posture had evolved in the Archosaur lineage during the Triassic under selective pressures associated with locomotor efficiency on dry ground, the ability to sustain activity over longer distances and at higher speeds. Sprawling competitors allowed. When the Carnian wet phase transformed large areas of the Pangaean landscape into saturated, topographically complex terrain, the precise foot placement and stable, energy-efficient gait enabled by erect posture proved advantageous in ways that dry-ground locomotor selection had not specifically anticipated. Moving through flooded, debris-strewn environments required controlled, deliberate limb placement that the erect, narrow-based gait of early archosaurs facilitated more effectively than the wide, sprawling gait of their amphibian contemporaries. At the same time, the elevated metabolic rates suggested by dinosaur bone histology, reflecting a physiology intermediate between ectothermy and full endothermy, conferred thermal independence in environments where solar basking was unreliable. Due to persistent cloud cover, an animal that could maintain muscular performance and sensory acuity across a range of ambient temperatures without depending on external heat sources was functionally more versatile in the thermally variable, light-limited conditions of the Carnian than an animal whose performance was directly coupled to environmental temperature. This thermal versatility was not a new trait generated by the wet phase. It was a pre-existing characteristic of the Archosaurian lineage that the Carnian's specific conditions made selectively decisive. The radiation of early mammal-like animals, the cynodonts and their descendants, the lineage from which true mammals would eventually emerge, was similarly shaped by the selective filtering of the Carnian interval. Cynodonts had developed, during the Permian and early Triassic, a suite of physiological and anatomical characteristics associated with elevated metabolic rates. Differentiated dentition for more efficient food processing, a secondary palate allowing simultaneous breathing and eating, evidence of a diaphragm-like structure enabling more powerful ventilation, and likely some degree of body insulation. These characteristics were associated with higher energetic throughput. Cynodonts processed food more rapidly and maintained higher activity levels than most of their contemporaries. During the Carnian wet phase, This high metabolic strategy carried specific costs and benefits. The costs were energetic. Maintaining a high metabolic rate requires continuous food intake, and in environments where food availability was episodically disrupted by flooding and ecological instability, high metabolic animals faced greater risk of starvation during food scarcity intervals. This cost likely contributed to the decline of larger cynodont lineages during the Carnian, as their absolute food requirements were difficult to meet during periods of ecological disruption. Smaller cynodonts, however, with lower absolute food requirements despite comparably high mass-specific metabolic rates, were better positioned to survive food scarcity intervals. The selective pressure of the wet phase thus operated as a body size filter within the cynodont lineage, favoring small, energetically flexible individuals and establishing the small-bodied, ecologically versatile body plan that would characterize early true mammals for tens of millions of years. The isolation of populations by flooding was a mechanism of evolutionary diversification that operated across multiple lineages simultaneously during the Carnian. When rising water levels fragment a previously continuous habitat into a mosaic of isolated patches, elevated ground separated by flooded lowlands, river islands surrounded by high discharge channels, habitat refugia isolated by expanding swamps, the populations occupying those patches become reproductively isolated from one another. Gene flow between them ceases. Each population evolves independently under the specific local conditions of its patch. Over sufficient generations, the genetic divergence between isolated populations accumulates to the point where, if those populations subsequently come into contact when water levels drop and connectivity is restored, they may no longer interbreed successfully. Speciation has occurred. This mechanism, allopatric speciation driven by habitat fragmentation, is well documented in modern biogeography and is particularly associated with dynamic environments in which habitat connectivity fluctuates over time. The Carnian wet phase created exactly the conditions for this mechanism to operate at continental scale. The expansion of flooding across lowland regions fragmented populations of terrestrial organisms across Pangaea, creating a mosaic of isolated evolutionary experiments. When conditions subsequently changed as they did, eventually toward the end of the Carnian and into the early Norian, and connectivity was restored across formerly flooded regions, the biosphere that emerged from isolation was more diverse than the one that had entered it. New species, differentiated during isolation, encountered one another in the newly reconnected landscape and engaged in ecological interactions, competition, predation, mutualism that had not previously existed. The pace of evolutionary change within isolated populations during the Carnian was not constant. Evolution accelerates under strong selective pressure and decelerates when selection is weak or inconsistent. The Carnian environment imposed strong, consistent selective pressure on the populations it isolated. The specific demands of flooded terrain, reduced light, high parasite loads, oxygen-depleted water bodies, and episodic food scarcity were applied continuously across the generations, maintaining directional selection on multiple traits simultaneously. Under these conditions, evolutionary change within isolated populations could proceed rapidly by geological standards, measurable morphological and physiological divergence accumulating across intervals of tens of thousands rather than hundreds of thousands of years. Evidence for this accelerated evolutionary tempo during the Carnian is visible in the pattern of faunal turnover recorded in the fossil record. Assemblages from early Carnian deposits differ substantially from those of late Carnian and early Norian age, not only in which species are present, but in the morphological characteristics of related species, suggesting that significant evolutionary change had occurred within lineages across the interval. The rate of new species appearances' first occurrences in the stratigraphic record is elevated during the Carnian relative to adjacent intervals, consistent with a period of accelerated speciation driven by environmental disruption and population isolation. The Archosaurian lineage diversified substantially during and immediately following the Carnian interval. Within the broader Archosaur group, the wet phase appears to have acted as a selective sieve, eliminating lineages with narrow ecological tolerances and body plans poorly suited to environmental variability, while allowing those with greater ecological flexibility to persist and subsequently radiate. The crocodilomorph lineage, the group that would eventually give rise to modern crocodilians, diversified during the late Triassic in ways that reflect adaptation to semi-aquatic environments. Early crocodilomorphs were not the massive, ambush predatory animals of the modern fauna. They were smaller, more terrestrially capable, and ecologically diverse, a radiation that appears to have been facilitated by the ecological opportunities created by the Carnian disruption of previously dominant faunas. The pterosaurs, the first vertebrates to achieve powered flight, appeared during the late Triassic, with the oldest unambiguous pterosaur material dating to approximately 210 to 215 million years ago. Their origins remain somewhat obscure in the fossil record, but their appearance in the aftermath of the Carnian interval is consistent with a pattern in which the ecological disruption of the wet phase opened evolutionary space for new body plans to emerge and diversify. Flight, as a locomotor strategy, confers access to spatial resources unavailable to terrestrial animals, elevated perches, aerial prey, dispersal across barriers that ground-dwelling organisms cannot cross. In a landscape fragmented by flooding, the ability to disperse across water barriers would have been an extraordinary advantage. The long-term evolutionary legacy of the Carnian wet phase is therefore not simply a list of which lineages survived and which did not. It is a reorganization of the developmental and physiological trajectories of the surviving lineages, a redirection of evolutionary momentum that persisted for tens of millions of years beyond the wet phase itself. The dinosaurs that would come to dominate Jurassic and Cretaceous ecosystems were not the product of a sudden evolutionary innovation that occurred after the Carnian. They were the product of selection that had been operating through the Carnian, refining the characteristics that would prove decisive in the drier, more competitive world that followed. The rain did not merely accompany this evolutionary process, it caused it, by imposing specific, sustained, and geographically variable selective pressures on the entire terrestrial biosphere of Pangaea. The Carnian wet phase redirected the course of vertebrate evolution in ways that are traceable forward through geological time to the world that exists today. Every living reptile, every bird, every mammal carries within its biology the downstream consequences of selection pressures that operated in the flooded lowlands and isolated uplands of Carnian Pangaea. During an interval when the sky was rarely clear and the water rarely stopped, the atmosphere of Carnian Pangaea was not a passive envelope of gas overlying a wet landscape. It was an active, energetic system, a fluid medium in constant motion, organized by thermal gradients driven by the differential heating of land and ocean surfaces, and loaded with moisture at concentrations that exceeded any sustained state documented in the modern instrumental record. To understand the storms that formed within this atmosphere, it is necessary to understand the thermodynamic principles that govern storm development, and to apply those principles to boundary conditions, sea surface temperatures, atmospheric moisture content, continental geometry, and radiative forcing that were substantially different from those of the present day. Convective available potential energy, abbreviated CAPE, is the quantity that atmospheric scientists use to measure the potential for deep convective storm development in a given atmospheric column. It represents the energy available to a parcel of air that is lifted from the surface, the energy derived from the buoyancy of warm, moist air relative to the cooler, drier air surrounding it at higher altitudes. High CAPE values indicate an atmosphere in which lifted air parcels will continue rising vigorously to great altitudes, producing deep cumulonimbus clouds, intense precipitation, and severe weather. Modern severe thunderstorm environments over the central United States environments, capable of producing tornadoes, large hail, and intense rainfall, are characterized by CAPE values ranging from approximately 2,000 to 5,000 joules per kilogram of air. The atmospheric conditions over equatorial Pangaea and the adjacent Tethys Ocean during peak Carnian rainfall intervals would have produced CAPE values substantially exceeding modern severe storm benchmarks. Sea surface temperatures in the range of 34 to 36 degrees Celsius generate evaporation rates and lower tropospheric moisture contents that, when combined with the strong lapse rates, the rate at which temperature decreases with altitude characteristic of tropical atmospheric profiles, produce CAPE values that current climate models suggest could have reached or exceeded 8,000 to 10,000 joules per kilogram in the most extreme conditions. These values are not merely higher than modern severe storm environments by a moderate increment. They represent an atmosphere in which convective storms, once initiated, would have developed with exceptional rapidity and intensity, reaching the upper troposphere in timeframes shorter than modern equivalents and sustaining deep convection for longer durations. The vertical extent of these storm systems is a critical parameter. Modern large cumulonimbus clouds reach altitudes of 12 to 15 kilometers in tropical environments, where the tropopause, the boundary between the troposphere and the stratosphere, acts as a limiting lid on convective development. The height of the tropopause is itself temperature dependent. Warmer surface temperatures raise the tropopause, allowing convective systems to develop to greater altitudes before encountering the stable stratospheric layer that suppresses further ascent. In the warmer Triassic atmosphere, tropopause heights over equatorial regions may have been 2 to 3 kilometers higher than modern tropical values, allowing Carnian convective systems to reach altitudes of 17 to 18 kilometers deeper penetration into the upper atmosphere, more vigorous updraft velocities, and more intense precipitation at the surface. Lightning generation within deep convective systems depends on the separation of electrical charge between ice crystals and Graupel soft hail in the mixed phase region of the cloud, where both water droplets and ice particles coexist at temperatures between approximately 0 and minus 40 degrees Celsius. In deeper, more vigorous convective systems, this mixed phase region is larger, updraft velocities carrying particles through it are higher, and charge separation occurs more rapidly and at greater magnitude. The result is a higher flash rate, more lightning discharges per unit time, and potentially higher peak current per discharge, as larger charge separations produce more energetic breakdown events. Reconstructing actual lightning flash rates for the Carnian atmosphere is not directly possible from the geological record. Lightning does not leave a continuous stratigraphic record in the way that sediment does. However, indirect evidence is available. Fulgurites, glassy tubes of fused mineral material formed when lightning strikes sandy or silty substrate, are preserved in geological formations of various ages, and their abundance relative to the volume of sediment examined can provide a rough proxy for historical lightning frequency. Additionally, The nitrogen fixation driven by lightning discharge leaves chemical signatures in the form of nitrate enrichment in paleosols and marine sediments. Elevated nitrate concentrations in Carnian age deposits from multiple regions are consistent with higher than modern lightning activity, though the magnitude of this enhancement remains a subject of ongoing research. Beyond individual convective cells, the Carnian atmosphere organized storm activity at larger scales. Mesoscale convective systems organized clusters of thunderstorms that develop their own internal circulation and persist for hours to days, form when individual convective cells interact with one another and with the broader atmospheric flow. In modern tropical environments, mesoscale convective systems are responsible for a disproportionate fraction of total annual rainfall. Despite occupying a smaller fraction of total storm hours than isolated convective cells, they are more efficient at producing precipitation because their organized internal circulation with broad, sustained updraft regions and compensating downdrafts arranged in a structured pattern allows them to process larger volumes of atmospheric moisture than isolated storms. In the moisture-rich Carnian atmosphere, mesoscale convective systems would have been larger, more persistent, and more geographically extensive than their modern analogues. Systems that in the modern tropics might span 200 to 500 kilometers and persist for 12 to 24 hours could, under Carnian thermodynamic conditions, have achieved lateral extents of 500 to 1,000 kilometers or more and persisted for multiple days before the moisture supply sustaining them was exhausted, which, given the continuous evaporation from the warm Tethys surface beneath them, may have occurred rarely or not at all during the peak wet phase. The interaction of these large convective systems with the orographic features of Pangaea created precipitation patterns of extreme spatial variability at regional scales. Mountain ranges intercepted moisture-laden airflow and forced it upward, triggering precipitation on windward slopes at rates that could substantially exceed the already elevated background values of the open atmosphere. Precipitation rates during active orographic enhancement events, when a large, organized storm system encountered a significant topographic barrier, may have reached values of 100 mm per hour or more over limited areas. At these rates, the volume of water arriving at the surface in a single hour exceeds the annual precipitation of many modern arid regions. The geomorphic consequences of such extreme precipitation events were immediate and dramatic at local scales. Saturated hill slopes, unable to accommodate additional water infiltration, failed in mass movements, debris flows, and landslides that mobilized soil and rock simultaneously, transporting mixed sediment-water slurries downslope at velocities of several meters per second. Modern catastrophic debris flows triggered by extreme rainfall events provide an analog for these processes, and the sedimentary deposits they produce poorly sorted, chaotically structured accumulations of mixed grain sizes are recognizable in the geological record. Triassic formations in several mountain belt regions preserve exactly these characteristics in intervals corresponding to the Carnian wet phase, providing direct physical evidence of the extreme precipitation events that the atmospheric conditions of the period were capable of generating. Scientists reconstructing the atmospheric conditions of the Carnian draw on multiple lines of evidence beyond sedimentary records. Stable isotope analysis of carbonate minerals precipitated from ancient water bodies, specifically the ratio of oxygen 1:8 to oxygen 1:6, which varies with the temperature and evaporative history of the water from which the carbonate formed, provides constraints on past water cycle intensity. Paleosol carbonate nodules, which form in soils under specific moisture and temperature conditions, record the isotopic composition of ancient soil water and rainfall, allowing reconstruction of past precipitation amounts and seasonality in continental interiors. Biomarker molecules, organic compounds produced by specific biological sources and preserved in ancient sediments, provide additional information about past environmental conditions. Certain biomarkers indicate the activity of specific microbial communities that thrive only under particular redox or temperature conditions, allowing reconstruction of water column chemistry in ancient lake and marine environments. The integration of these multiple proxy records, each with its own uncertainties and limitations, but collectively convergent on a consistent picture, provides the empirical foundation for current understanding of Carnian atmospheric conditions. The picture that emerges from this evidence is of an atmosphere operating at the upper limits of what the physical constraints of the Triassic Earth permitted, not an atmosphere in some anomalous, physically impossible state, but one in which the thermodynamic engine of the hydrological cycle was running at maximum capacity given the boundary conditions of sea surface temperature, continental geometry, and atmospheric composition that characterized the period. The storms were large because the ocean was warm. The ocean was warm because greenhouse gas concentrations were elevated. The greenhouse gas concentrations were elevated because of volcanic activity associated with the tectonic configuration of Pangaea. Each element of this causal chain was connected to the others, and the storms that resulted illuminating entire continental interiors with continuous lightning, depositing water at rates that reshaped landscapes in real time, organizing into systems that persisted for days across areas the size of modern nations with a visible, atmospheric expression of a planet operating under a fundamentally different climatic regime than the one that exists today. The sky above Carnian Pangaea, as reconstructed from this evidence, was rarely what modern observers would recognize as clear. Even in periods between the most intense convective events, the lower and middle troposphere carried sufficient moisture to maintain extensive stratiform cloud cover, broad, layered sheets of cloud that produced continuous light to moderate precipitation without the intense convective activity of the deep cumulonimbus systems. This stratiform precipitation, falling steadily at rates of 1 to 5 millimeters per hour across areas of millions of square kilometers, contributed a substantial fraction of the total water delivered to the surface during the wet phase. It was less dramatic than the convective storms, but more continuous, a persistent, gentle inundation that maintained soil saturation and water table levels between the more intense events. The visual character of the sky under these conditions, layers of gray cloud at multiple altitudes, the lower levels moving faster than the upper, occasional breaks revealing only higher cloud layers. Beyond was the defining optical environment of the Carnian world. Light reached the surface diffuse and attenuated, stripped of the directional character it has under clear skies. Shadows were absent or indistinct. Color contrast at the surface was reduced. The world below the clouds was uniformly illuminated, uniformly wet, and perpetually overcast, a condition that persisted not for days or seasons, but across geological time, encoding itself into the biology of every organism that lived within it and into the rock of every formation that formed beneath it. Light is not simply a convenience for living organisms, it is a foundational resource, the energy source that drives photosynthesis, the signal that synchronizes biological clocks, the medium through which most vertebrate animals gather the majority of their environmental information. When the availability of light changes fundamentally and persistently, the biological systems that depend on it do not remain static. They adjust at the physiological level within individual organisms and at the evolutionary level across populations to the new regime of illumination that the environment provides. The Carnian world, beneath its persistent overcast, was a world in which the quantity, quality, and predictability of light at the surface were all substantially altered from the conditions under which most of the fauna and flora of the time had originally evolved. The biological responses to this altered light environment were pervasive, and their traces are visible both in the morphology of Carnian organisms and in the ecological structures of the communities they formed. The reduction in total solar irradiance at the surface under persistent cloud cover is quantifiable in approximate terms. Modern measurements of surface solar radiation under overcast conditions, dense stratiform cloud cover of the type that would have characterized the Carnian atmosphere during periods of active rainfall, show reductions of 70 to 90% relative to clear sky values at the same latitude and season. Under a clear tropical sky, surface irradiance at solar noon approaches 1000 watts per square meter. Under dense overcast, this value drops to 100 to 300 watts per square meter, sufficient to support photosynthesis in adapted plant communities, but substantially below the light saturation point of most high-productivity plant species evolved under clearer conditions. The photosynthetic implications of this reduction were significant, but not catastrophic for adapted plant communities. Plants are capable of acclimating to lower light environments through several mechanisms, increasing the density of chlorophyll per unit leaf area to capture more of the available photons, expanding leaf area to intercept more total light, and reducing the light compensation point, the irradiance level at which photosynthetic carbon fixation exactly balances respiratory carbon loss through adjustments in cellular metabolism. Shade-adapted plant forms typically have larger, thinner leaves with higher chlorophyll content per unit area than their sun-adapted counterparts, and they maintain positive carbon balance at irradiance levels that would leave sun-adapted species in net carbon deficit. The plant communities of the Carnian wet zone, dominated by ferns, horsetails, and early conifers, included many lineages with evolutionary histories in forest understory environments, where light availability was inherently limited by canopy interception even under clear skies. These lineages were pre-adapted, to varying degrees, for low-light photosynthesis. Their physiological responses to the reduced irradiance of the Carnian overcast were therefore less extreme than might have been required of plant communities dominated by high-light specialists. The ferns that carpeted the flooded lowlands continued to photosynthesize effectively under diffuse, attenuated illumination, maintaining the primary productivity that supported the entire terrestrial food web. For animals, the reduction in light availability had consequences operating through multiple physiological pathways. The most immediate was visual, the capacity to detect and respond to environmental information encoded in reflected light. Visual systems are tuned by evolution to the typical illumination conditions of the environments in which they operate. Animals active in bright daylight possess visual systems with high spatial acuity, color discrimination across broad spectral ranges, and rapid temporal resolution, the ability to detect fast-moving objects against a bright background. Animals active in dim conditions possess visual systems with high photon capture efficiency, large pupils, high rod-to-cone ratios in the retina, and in some lineages, tapetum lucida, the reflective layer behind the retina that gives nocturnal animals their characteristic eyeshine. In the dim, diffuse illumination of the Carnian surface environment, the selective advantage of high-acuity daylight vision was reduced relative to its value under clear sky conditions. The contrast differences between objects that daylight vision exploits, the sharp shadow boundaries, the color contrasts, the specular highlights on shiny surfaces, were all attenuated under overcast illumination. Visual predators that relied on detecting fast-moving prey against a bright background would have found their detection distances reduced and their reaction times to moving stimuli extended. Visual prey animals that relied on detecting the shadow of an approaching predator, a common anti-predator mechanism in open water aquatic environments, would similarly have found this cue less reliable under the uniform, shadowless illumination of the overcast sky. The selective pressure toward enhanced non-visual sensory capabilities in Carnian fauna was therefore operating not only through the mechanisms of water turbidity and acoustic masking by rain, but through the direct attenuation of the visual information available in the aerial environment. Olfaction, the detection of chemical signals dissolved in air or water, does not depend on light and would have been unaffected by cloud cover in terms of the signal itself, though wind patterns associated with storm systems could disperse olfactory cues more rapidly and unpredictably than the calmer conditions of a clear sky environment. Mechanoreception, the detection of substrate vibration, pressure waves in water, and air pressure fluctuations, similarly operates independently of light availability. Animals with enhanced investment in these sensory modalities at the expense of visual system complexity would have been better calibrated to the actual information environment of the Carnian landscape. Fossil evidence for sensory system evolution is necessarily indirect soft tissue structures responsible for olfaction, mechanoreception, and electroreception do not preserve in most fossil contexts. However, skull morphology provides some information. The relative sizes of olfactory bulb endocasts, the arrangement of sensory foramina through which nerve branches innervating facial sensory organs pass, and the dimensions of structures associated with inner ear function can all be estimated from well-preserved cranial material. Triassic vertebrate skulls. From this interval show, in several lineages, characteristics consistent with investment in chemosensory and mechanosensory systems, large olfactory regions relative to overall brain size, well-developed lateral line canal systems in aquatic forms, and inner ear morphologies suggesting sensitivity across a broad range of mechanical frequencies. Circadian biology, the internal timekeeping systems that synchronize an organism's physiology and behavior to the 2-4-hour cycle of day and night, was also affected by the altered light environment of the time-paced. Carnian. Circadian rhythms in most organisms are entrained to the environmental light cycle through photoreceptive structures that detect the daily pattern of light onset and offset. The consistency and reliability of this entraining signal its predictability from day to day is critical for maintaining accurate circadian timing. Under clear skies, the daily light cycle is highly predictable. Dawn and dusk occur at consistent times, and the pattern of increasing and decreasing irradiance across the day provides a strong, unambiguous entraining signal. Under persistent overcast, this signal is degraded. The total daily light dose is reduced, the contrast between the brightest part of the day and the dimmest is compressed, and on days of continuous thick overcast, the distinction between day and night in terms of light intensity may be relatively subtle, particularly beneath a dense forest canopy in a flooded lowland, where the additional attenuation of canopy interception further reduced the already diminished surface irradiance. Circadian systems that had been calibrated to strong, reliable daily light signals would have experienced difficulty maintaining precise entrainment under these conditions, potentially leading to desynchronization of physiological processes, immune function, hormone secretion, digestive activity that depend on accurate circadian timing for optimal performance. The evolutionary response to this challenge would have been selection for circadian systems capable of maintaining robust rhythmicity under weak or inconsistent light signals and systems with stronger endogenous oscillators less. dependent on continuous external reinforcement for their accuracy. Whether this selective pressure is detectable in the molecular architecture of circadian clock genes in the descendants of Carnian survivors is a question that molecular evolutionary analysis might eventually address, though disentangling this signal from the many other selective pressures acting on circadian biology across 230 million years of subsequent evolution presents formidable methodological challenges. The thermal environment at the surface of the Carnian world was shaped by cloud cover in ways that extended beyond the simple reduction of solar input. Clouds are not only reflectors of incoming solar radiation, they are also strong absorbers and emitters of long-wave thermal radiation. A cloudy sky emits substantially more long-wave radiation downward toward the surface than a clear sky, because the cloud base, at temperatures significantly warmer than the effective radiating temperature of a clear sky, emits energy according to its own temperature. This downward long-wave emission partially compensates for the reduction in absorbed solar radiation, maintaining surface temperatures closer to their clear sky values than would otherwise be expected given the reduction in solar input. The net effect of persistent cloud cover on surface temperature is therefore a compression of the diurnal temperature range, the difference between daytime maximum and nighttime minimum temperatures. Under clear skies, daytime solar heating warms the surface significantly above nighttime values, producing a large diurnal temperature swing. Under persistent overcast, daytime temperatures are lower, less solar energy is absorbed, but nighttime temperatures are higher. More long-wave energy is emitted downward by the clouds. The result is a narrower daily temperature range, with days that are less warm and nights that are less cold than their clear sky equivalents at the same latitude and season. For ectothermic animals whose body temperature tracks environmental temperature, this compressed diurnal range had direct physiological consequences. The ability to achieve high body temperatures through basking and the necessity of tolerating low nighttime body temperatures were both reduced in the Carnian environment. Ectotherms in this setting experienced a more thermally stable environment than their descendants in later, clearer climates with temperatures that varied less across the day and that remained within a narrower range overall. This stability reduced the selective pressure for behavioral thermoregulation, the active movement between warm and cool microhabitats to maintain optimal body temperature, because the range of available temperatures in the environment was itself narrowed. The psychological dimension of a world without clear skies, a concept that carries inevitable anthropomorphic implications, can nevertheless be approached in functional terms when considering the sensory experience of Carnian fauna. For animals with well-developed visual systems, the absence of direct sunlight, the perpetual grey of the overcast canopy, and the reduced contrast of the visual environment define the totality of normal experience. There was no memory of clearer skies, no expectation of sunlight that failed to arrive. The dim, diffuse illumination of the Carnian surface was not experienced as deprivation by the organisms that inhabited it. It was simply the world, the only world those lineages had known for as many generations as evolutionary memory extends, and the world to which every aspect of their biology had been calibrated by the accumulated selection of millions of years of life beneath permanent clouds. Environmental transitions of the magnitude of the Carnian pluvial episode do not end abruptly. The atmospheric and oceanographic systems that sustained the wet phase for millions of years were not switched off by a single geological event. They were gradually undermined, their thermodynamic fuel supplies reduced, their organizational structure weakened, their capacity to maintain the moisture, fluxes, and convective intensities that had defined the Carnian atmosphere progressively diminished by a combination of processes operating at different rates and through different mechanisms. across a geological interval that itself spanned tens of thousands to hundreds of thousands of years. The transition from the wet phase to the comparatively drier conditions of the Norian stage that followed was, by geological standards, relatively rapid. By the standards of any biological timescale, it was extraordinarily slow, a change so gradual that no individual organism and no population across the span of its existence could have perceived it as change at all. The primary driver of the eventual weakening of the wet phase was tectonic. Pangaea was not a static landmass. Throughout the Triassic, the forces driving plate motion, the slow convective circulation of material in the Earth's mantle, were continuing to operate beneath the supercontinent, developing the extensional stresses along incipient rift zones that would eventually fragment Pangaea into the separate continental plates of the modern world. As rifting progressed during the late Carnian and into the Norian, the geometry of the continental surface changed. New seaways began to develop along rift zones, altering the circulation patterns of the Tethys and Panthalassic oceans and modifying the pathways along which warm, moisture-laden air was transported from ocean surfaces into the continental interior. The opening of incipient rift basins along what would eventually become the Central Atlantic created new marine connections between previously separated water bodies, modifying sea surface temperature distributions and altering the thermal gradients that drove atmospheric circulation. As the geometry of the ocean changed, the specific wind patterns that had been delivering moisture to the interior of Pangaea were modified. Regions that had previously been positioned within the moisture transport pathways of the Carnian atmospheric circulation began to receive less oceanic moisture as those pathways shifted. The atmospheric engine that had sustained the wet phase did not stop running. Its fuel supplied the thermal energy of warm ocean surfaces, and the moisture they evaporated was gradually redirected by the changing shape of the ocean basins beneath it. Simultaneously, volcanic activity associated with the early stages of Central Atlantic magmatic province emplacement was beginning to shift in character. The most intense phases of flood basalt volcanism, during which enormous volumes of lava were extruded onto the surface over geologically brief intervals, releasing correspondingly large pulses of carbon dioxide and sulfur dioxide into the atmosphere, were approaching their peak during the latest Triassic. The sulfur dioxide released during intense volcanic episodes has a cooling effect on climate, in contrast to the warming effect of carbon dioxide, because sulfate aerosols formed from volcanic sulfur reflect incoming solar radiation back to space. The interplay between volcanic carbon dioxide warming and volcanic sulfate cooling during the transition out of the Carnian wet phase was complex and not yet fully resolved by current research. But the net effect across the late Carnian and Norian appears to have been a gradual shift towards somewhat drier conditions across many regions of Pangaea. The physical expression of this climatic transition in the sedimentary record is recognizable and has been documented in multiple geographic regions. In the Germanic basin of Central Europe, the dark, organic-rich, grey sediments characteristic of the wet phase transition upward into redder, more oxidized deposits, the color change reflecting the shift from waterlogged, reducing conditions, to better drained, oxidizing soils as rainfall decreased and water tables dropped. In the Chinle Formation of what is now the American Southwest, sedimentological analysis across the Carnian-Norian boundary interval records a shift from predominantly fluvial depositional environments wide, high-discharge river systems to more varied assemblages, including aeolian deposits and oxidized paleosols, indicating the development of seasonal dry intervals and the retreat of perennial flooding from previously inundated regions. Paleosol morphology is particularly informative about this transition. Soils forming under persistently wet conditions develop specific characteristics. Glaying, the bluish-gray coloration produced by iron reduction in waterlogged, oxygen-depleted conditions pronounced leaching of soluble minerals, and the accumulation of organic matter that aerobic decomposers cannot break down. Soils forming under seasonally dry conditions develop different characteristics. Carbonate nodules precipitated from soil water that evaporates during dry seasons, reddish coloration from oxidized iron compounds, and more complex horizon structures reflecting alternating wet and dry intervals. The transition from gleed organic-rich paleosols to carbonate-bearing, oxidized paleosols across the Carnian-Nourian boundary in multiple continental sections records, directly and mineralogically, the retreat of the wet phase from specific geographic regions. For the biological communities that had spent millions of years calibrating themselves to the conditions of the wet phase, the retreat of the rain was not a straightforwardly positive development. It was a new set of selective pressures, as novel and as demanding, in their own way, as the onset of the wet phase had been for the preceding fauna. Organisms that had evolved waterproof skin impermeable to desiccation, physiological tolerance for reduced light, and reproductive strategies compatible with permanent standing water found themselves, over the course of the transition, in environments that were progressively less consistent with those adaptations. The large temnospondyle amphibians, the dominant predators of the flooded lowlands, were among the most vulnerable to the drying transition. Their reproductive biology was tightly coupled to permanent water. Their metabolic physiology required moisture for cutaneous gas exchange. Their body plans, optimized for movement through shallow water and soft substrate, were less effective on the firmer, drier ground that was emerging as water tables dropped. As the flooded lowlands contracted, the habitat that sustained the giant amphibian fauna contracted with them. Populations that had been continuous across vast floodplain areas became fragmented into the remaining wet refugia, isolated marshes, river margins, and residual lake systems where water persisted after the surrounding lowlands had drained. The contraction of wetland area did not immediately eliminate the temnospondyle fauna. Several lineages persisted well into the Jurassic and, in some interpretations of the fossil record, into the early Cretaceous in Gondwanan refugia, where wet conditions were maintained by local geographic and climatic factors. But the trend across the Nourian and into the Jurassic was one of progressive decline, a slow reduction in the geographic range, species diversity, and ecological dominance of the group that had presided over the Carnian flooded ecosystems. The retreating rain was withdrawing the environmental conditions that had sustained them, and the world that was emerging in the wake of the wet phase belonged increasingly to lineages that had different requirements and different capabilities. The early reptilian lineages, including the Dinosaurian and crocodilomorphan archosaurs, were positioned more favorably for the transition. Their impermeable scaled skin reduced the risk of desiccation as humidity declined. Their reproductive strategy, laying eggs with more resistant shells or membranes than those of amphibians, reduced their dependence on standing water for reproduction. Their locomotor systems, optimized for movement on firm ground, became more effective as substrates dried and firmed. The transition from wet phase to post-wet phase was, for these lineages, not an environmental crisis, but an expansion of opportunity, the emergence of new habitat types that their pre-existing adaptations allowed them to exploit. The vegetation communities of the transitional period reflect the ecological reorganization underway across the landscape. As waterlogged lowlands drained, the fern and horsetail communities that had dominated the wettest zones were replaced, progressively, by conifer-dominated vegetation capable of tolerating the drier, better drained soils of the newly emerged terrain. Early conifers, members of lineages that had persisted in the better drained uplands throughout the wet phase, expanded their ranges downslope into terrain that was becoming suitable for the first time in millions of Vengeta years. This vegetational shift altered the structural character of the landscape. From the low, fern-dominated ground cover of the swamps to the taller, more architecturally complex communities of conifer-dominated forests with their deeper root systems, higher canopy, and more complex structural layering. The new vegetation provided different ecological resources for the animals moving into the transitional landscape. Conifer forests offered elevated foraging opportunities, more varied structural habitats, and, eventually, the seed resources that would support new guilds of herbivores. The insects that had been so abundant in the humid fern-dominated ecosystems partially diversified into new niches offered by the conifer flora pollination associations, wood-boring habits in conifer trunks, leaf feeding on conifer needles. The food web was reorganizing around new primary producers, and the animals that could exploit those producers were the ones that would inherit the post-Carnian landscape. The transition was not linear or geographically uniform. Some regions retained wet conditions longer than others, depending on local topography, proximity to remaining moisture sources, and the specific trajectory of tectonic changes in their area. In these persistent wet refugia, the Carnian fauna, the large amphibians, the wet-adapted plant communities, the parasites and invertebrates, calibrated to high humidity conditions, survived for longer than in the regions where drying was most rapid. This geographic heterogeneity in the pace of transition created a mosaic of ecological conditions across the late Triassic landscape. Wet refugia embedded within a matrix of progressively drying terrain, with the biological communities of each reflecting the specific local history of their site's transition out of the wet phase. At the boundaries between these zones where drying terrain met persisting wetlands, ecological interactions between the fauna of the two regimes occurred. Early dinosaurs and crocodilomorphs moving into newly dry terrain encountered the remnant populations of the Carnian fauna at the edges of their contracting refugia. Competition, predation, and the gradual ecological displacement of wet phase specialists by post-wet phase generalists played out across these boundary zones across hundreds of thousands of years. The slow, geographically diffuse front of a biological transition that had no single location or moment, but that was, across geological time, as consequential as any of the more abrupt transitions that the fossil record preserves. The rain retreated the way it had arrived, gradually, unevenly, leaving behind a landscape transformed in ways that would only become fully apparent in the geological record assembled by the world that followed. The world that emerged from the long shadow of the Carnian wet phase was not the world that had preceded it. The biological communities, the physical geography, the atmospheric composition, and the ecological relationships of the post-Carnian Pangaea were all different, in some cases subtly, in others fundamentally from their pre-Carnian equivalents. The wet phase had not merely passed over the Triassic landscape like weather, leaving it essentially unchanged once the rain stopped. It had reorganized it selectively, eliminating some lineages, fragmenting and diversifying others, altering the competitive landscape in ways that persisted long after the specific environmental pressures that had produced them had weakened. The dinosaurs that began to radiate more broadly across Pangaea in the Nourian stage and into the Jurassic were not expanding into the same world their early Carnian ancestors had inhabited. They were expanding into a world that the Carnian had prepared for them through mechanisms that were biological, ecological, and evolutionary simultaneously. The Norian stage, beginning approximately 227 million years ago and extending to roughly 208 million years ago, is the geological interval in which the faunal transition from Carnian-dominated to dinosaur-dominated terrestrial ecosystems becomes most clearly legible in the fossil record. The change is not instantaneous at the Carnian-Norian boundary. It unfolds across stratigraphic sections spanning millions of years, with the relative abundance of dinosaur material increasing progressively relative to the large pseudosuchian archosaurs, dicynodonts, rhynchosaurs, and temnospondyls that had characterized earlier Triassic faunas. By the late Norian, in many geographic regions, dinosaurs had become numerically dominant among large-bodied terrestrial vertebrates, a position they had not occupied during the Carnian itself. The mechanisms underlying this faunal transition remain a subject of active scientific debate. Two broad interpretive frameworks have been proposed and continue to generate research and discussion. The first, sometimes called the competitive displacement hypothesis, proposes that dinosaurs actively outcompeted the incumbent fauna through superior physiological, locomotor, or ecological capabilities, that they were, in some measurable sense, better suited to the post-Carnian environment and displaced their competitors through direct ecological competition. The second framework, sometimes called the opportunistic radiation hypothesis, proposes that dinosaurs did not actively displace the incumbent fauna, but rather expanded into ecological space that was opened by the extinction of non-dinosaurian lineages through environmental causes unrelated to dinosaurian. Competitive superiority, that they were beneficiaries of others' misfortune rather than architects of their own dominance. Current evidence does not conclusively support either framework to the exclusion of the other, and the most accurate interpretation likely involves elements of both. The environmental stresses of the Carnian wet phase and its aftermath, habitat contraction, disease, dietary resource loss, reproductive failure in seasonally variable conditions, drove the decline of lineages that were ecologically dependent on the wet phase conditions. This decline opened ecological space. The dinosaurian lineage, with its pre-existing advantages in locomotor efficiency, metabolic versatility, and reproductive independence from permanent water, was positioned to expand into that space more rapidly and effectively than other surviving lineages. Competition and opportunity were not mutually exclusive mechanisms. They operated simultaneously, reinforcing each other across the ecological transition. The diversification of dinosaurs during the Norian proceeded along multiple ecological axes simultaneously. In body size, early Norian dinosaurs ranged from small, lightly built bipeds of less than 1 kilogram to animals approaching several hundred kilograms, a body size range that expanded further into the Jurassic and Cretaceous, but that was already substantially greater by the late Triassic than it had been during the early Carnian. In dietary ecology, the dinosaurian lineage diversified into both carnivory and herbivory during the Norian, with the sauropodomorph lineage, the group that would eventually produce the largest terrestrial animals in Earth's history, already establishing herbivorous body plans of significant size by the late Triassic. The sauropodomorphs are particularly instructive as an example of post-Carnian ecological expansion. Early members of this lineage, such as Plateosaurus from late Triassic formations in what is now Germany and Switzerland, reached body lengths of 6 to 10 meters and masses estimated at several hundred kilograms to over a ton, body sizes that made them among the largest terrestrial animals of their time. Their dentition was adapted for processing plant material. Leaf-shaped teeth with coarse serrations suited to cropping vegetation, and their postcranial anatomy included features associated with the processing of large volumes of low-quality plant food. elongated necks allowing access to vegetation at various heights, large body cavities accommodating extensive digestive systems, and hind limb anatomy capable of supporting substantial body mass. The ecological success of early sauropodomorphs in the post-Carnian landscape was directly connected to the vegetational changes that had accompanied the retreat of the wet phase. The expanding conifer forests of the Norian provided elevated food resources foliage at heights accessible to animals with long necks and large bodies, but inaccessible to the lower browsing fauna of the preceding wet phase. The shift from fern-dominated, low-growing vegetation to taller conifer-dominated forest effectively raised the ceiling of the available herbivore niche space, creating an ecological opportunity that the sauropodomorphs, with their elongating necks and increasing body sizes, were evolving to exploit in real time. The forests that the post-Carnian drying had allowed to establish were, in this sense, both the product of the climatic transition and the ecological foundation of the herbivore radiation that followed it. Predatory dinosaurs diversified in parallel with their herbivorous relatives, tracking the increasing body sizes and biomass of available prey. The theropod lineage, the group encompassing all carnivorous dinosaurs, and, ultimately, modern birds, diversified during the Norian into a range of body sizes and ecological strategies. Small theropods, comparable in size and ecological role to the early Carnian dinosaurs from which they descended, continued to exploit the abundant small vertebrate and invertebrate prey of the terrestrial ecosystem. Larger theropods, capable of subduing substantial prey animals, were appearing in the fossil record by the late Triassic, the beginning of a trend toward large-bodied apex predation that would define dinosaurian carnivore ecology through the Jurassic and Cretaceous. The fate of the large pseudosuchian archosaurs, the dominant predators of many Triassic faunas prior to and during the Carnian across the Triassic-Jurassic boundary, is one of the most consequential extinction events in the Archosaurs Ds. The history of tetrapod vertebrates, though it is often overshadowed in popular accounts by the more dramatic End Cretaceous event. The End Triassic mass extinction, approximately 201 million years ago, was associated with the emplacement of the Central Atlantic Magmatic Province flood basalts, one of the largest volcanic events of the Mesozoic, and produced significant biodiversity loss across both marine and terrestrial environments. Among the casualties were most of the large pseudosuchian lineages that had coexisted with dinosaurs throughout the Triassic. The etosaurs, phytosaurs, and most large Rauisuchian lineages disappeared at or near the Triassic-Jurassic boundary, leaving ecological space that the dinosaurian lineage which survived the End Triassic event in substantially better shape than its pseudosuchian competitors rapidly filled during the earliest Jurassic. The reasons for the differential survival of dinosaurs relative to pseudosuchians across the End Triassic extinction are not entirely clear and continue to be investigated. Physiological differences, potentially including the more advanced respiratory system of dinosaurs, with its bird-like air sac system providing more efficient oxygen extraction from each breath, may have conferred advantages during the environmental disruption associated with flood basalt volcanism, which elevated atmospheric carbon dioxide concentrations and may have reduced atmospheric oxygen availability in some regions. Ecological flexibility, the ability to exploit a range of food resources and habitat types rather than depending on specific prey species or habitat conditions, may also have favored the dinosaurian lineage during an interval of ecological disruption. The crocodilomorph lineage, the other major surviving archosaurian group, also diversified during the post-Carnian and post-Triassic intervals, though along different ecological trajectories than the dinosaurs. Early crocodilomorphs of the late Triassic and early Jurassic were predominantly terrestrial, small to medium-bodied, and ecologically diverse, including cursorial predators, insectivores, and possible herbivores. The semi-aquatic, ambush predatory body plan that characterizes modern crocodilians was not the ancestral condition of the crocodilomorph lineage, but an evolutionary specialization that developed later as certain lineages reinvaded the aquatic habitats that the temnospondyls were vacating. The crocodilomorphs were, in this sense, ecological successors to the large amphibians in semi-aquatic predatory roles, a convergent evolution of ambush predation in waterside environments driven by the same ecological opportunities, with a different lineage filling the vacated niche. The mammals represented during the Triassic and Jurassic by small, predominantly nocturnal, insectivorous animals descended from the cynodont. Therapsids persisted throughout the Norian and into the Jurassic as a minor but evolutionarily significant component of terrestrial faunas. Their small body sizes, high metabolic rates, and likely nocturnal habits position them in ecological niches that the expanding dinosaurian fauna did not directly occupy. The sustained ecological pressure of dinosaurian dominance across the Jurassic and Cretaceous maintained mammals in small-bodied, ecologically marginal positions for over 150 million years, a constraint that was only released by the end Cretaceous extinction that removed the non-avian dinosaurs. The landscape itself was transforming across the post-Carnian interval in ways that were visible at continental scale. The drying of previously flooded lowlands created new soil surfaces, initially raw, poorly structured, and low in organic matter, but progressively colonized by vegetation and developed into the complex, nutrient-cycling soils that support high-productivity terrestrial ecosystems. River systems that had been broad, high-discharge, sediment-laden channels during the wet phase adjusted their morphology as discharge declined, narrowing their channels, reducing their sediment loads, and developing the more sinuous, laterally stable planform of rivers in equilibrium with lower, more seasonally variable discharge regimes. The geographic distribution of climate zones across Pangaea became more clearly differentiated as the wet phase weakened. Equatorial regions remained warm and relatively humid, supporting closed forest vegetation. Higher latitudes experienced more pronounced seasonality, warm, humid summers, and cooler, drier winters, producing open vegetation communities with greater structural diversity than the closed, year-round wet forests of the Carnian. The latitudinal climate gradient that characterizes modern Earth, tropical, subtropical, temperate, and polar zones arranged in broad bands of decreasing temperature and shifting precipitation seasonality, was becoming more clearly expressed across the Pangaean surface as the homogenizing influence of the wet phase atmospheric circulation weakened. Into this differentiating, drying, structurally diversifying world, the dinosaurs expanded not as a single, coordinated radiation, but as a collection of lineages responding independently to the ecological opportunities their specific environments offered. Each lineage tracked its own trajectory, driven by its own selective pressures in the specific habitats it occupied. The cumulative result of these independent radiations, viewed at the scale of geological time, was the establishment of dinosaurian ecological dominance across the terrestrial biosphere of the Jurassic, a dominance that had its roots not in any single moment of competitive triumph, but in the long, gradual, environmentally mediated process by which the Carnian wet phase had filtered and shaped the lineages that would inherit the world it left behind. The Carnian pluvial episode ended. The clouds thinned, the floodwaters retreated, and the supercontinent that had been saturated for millions of years began, slowly and unevenly, to dry. The giant amphibians diminished. The flooded forests contracted. The black swamps of Pangaea's interior, filled with sediment, compressed under the weight of subsequent deposition and transformed across hundreds of millions of years of burial, heat, and pressure into the coal seams and hydrocarbon deposits that underlie substantial portions of the modern world. The storm era closed, as all geological intervals close, not with a boundary that any living thing could perceive, but with the gradual accumulation of change across time so deep that it can only be measured in rock. What it left behind, however, did not disappear. The Carnian wet phase encoded its existence into the physical and biological fabric of the planet in ways that remain legible today in the geological record, in the evolutionary history of living organisms, in the chemistry of ancient sediments, and in the atmospheric and oceanographic systems that continue to operate in modified form under the same fundamental physical laws that governed the storms of 232 million years ago. Reading these traces requires the integration of multiple scientific disciplines and the application of analytical techniques that did not exist until recently. But the traces are there, preserved with the fidelity that only geological time and the laws of chemistry and physics can provide. The most volumetrically significant physical legacy of the Carnian wet phase is carbonaceous, the organic matter that accumulated in the waterlogged, anoxic environments of the Carnian floodplains and swamps, preserved from aerobic decomposition by the very conditions that the wet phase created. This organic material, buried under subsequent sediment loads and subjected to the increasing temperature and pressure of deeper burial, underwent a series of chemical transformations, collectively described as diagenesis and catagenesis, the progressive alteration of biological organic molecules into the simpler, more stable hydrocarbon compounds that form coal, oil, and natural gas. The coal measures of Europe, North America, and Asia that were deposited during and immediately following the Carboniferous period are the most extensively mined legacy of an earlier wet era, but Triassic Age organic-rich sediments also contribute to the global inventory of fossil carbon, and their formation is directly attributable to the accumulation conditions that the Carnian wet phase sustained. The burning of these fossil carbon deposits by human industrial civilization releases, over timescales of decades to centuries, carbon that was sequestered from the atmosphere during the Carnian and subsequent periods, carbon that was removed from the active carbon cycle by the same anoxic preservation conditions that the endless rain created. There is a geochemical symmetry, if not a moral one, in this process. The atmospheric conditions that the wet phase helped create by drawing down carbon into preserved organic matter are being partially reversed by the combustion of that matter hundreds of millions of years later, returning to the atmosphere carbon that the Carnian swamps removed from it. The storms of the Carnian contributed to the carbon burial that modulated atmospheric composition across the Mesozoic. The reversal of that burial is contributing to the atmospheric changes of the present. The fossil record of the Carnian interval preserves in bone and shell and plant material a direct physical archive of the biological communities that inhabited the wet phase world. Triassic fossil sites from formations spanning the Carnian interval, the Ishigualasto Formation of Argentina, the Chinle Formation of the American Southwest, the Schilf Sandstein and Gipskeiper Formations of Germany, the Manda Beds of Tanzania, marine sequences in the Alps and the Tethyan realm collectively document the faunal and floral composition of ecosystems before, during, and after the wet phase. Comparing these assemblages across the Carnian interval reveals the pattern of turnover, the species that disappeared, the lineages that diversified, the ecological structures that were assembled and dismantled that constitutes the biological record of the event. Fossil preservation in Carnian age deposits is influenced by the depositional environments of the wet phase itself. Fine-grained sediments deposited in low-energy aquatic environments, the still waters of lakes, backswamps, and floodplain pools are among the most favorable for the preservation of skeletal material because rapid burial in fine sediment protects bones from scavenging and physical dispersal before mineralization can occur. The abundant fine-grained sediments of the Carnian wet phase therefore created conditions favorable to fossil preservation across broad areas, and the Carnian fossil record, while incomplete as all fossil records are, is relatively rich in some taxonomic groups and geographic regions precisely because the depositional environments that the wet phase created were conducive to preservation. Geochemical proxies recorded in Carnian age sediments provide a chemical record of the wet phase that complements the physical and biological records. Carbon isotope excursions shifts in the ratio of carbon 1:3 to carbon 12 inches. Carbonate sediments are recorded at the onset of the Carnian wet phase in marine sequences from multiple geographic regions. These isotopic shifts reflect changes in the global carbon cycle associated with the environmental perturbation, changes in the rates of organic carbon burial, in the contribution of volcanic carbon to the atmosphere, and in the biological productivity of marine and terrestrial ecosystems. The carbon isotope record of the Carnian is one of the primary lines of evidence used by geochemists to identify and constrain the timing and duration of the wet phase in the absence of direct paleoclimate proxies. Oxygen isotope records from Carnian age carbonates provide information about past sea surface temperatures and the hydrological cycle intensity, specifically the degree to which evaporation and precipitation were fractionating oxygen isotopes in the water cycle. Heavier isotopic signatures in certain marine carbonates from the Carnian interval are consistent with elevated evaporation rates from warm ocean surfaces, providing independent geochemical support for the high sea surface temperatures inferred from other lines of evidence. The convergence of carbon isotope, oxygen isotope, sedimentological, and paleontological evidence from multiple geographic regions and multiple analytical approaches is what gives current reconstructions of the Carnian wet phase their scientific credibility, not any single line of evidence, but the coherent pattern that emerges when multiple independent records are examined together. Modern storm systems, examined against the reconstructed backdrop of Carnian atmospheric conditions, provide a sobering comparative perspective. The most intense tropical cyclones of the modern era, Category 5 hurricanes and equivalent typhoons, achieve maximum sustained wind speeds of 250 to 300 km per hour, produce central pressure drops of 50 to 100 hectopascals below ambient, and generate storm surges of 4 to 6 meters along coastlines they cross. These are, by any contemporary standard, events of extraordinary destructive power, capable of reshaping coastlines, devastating ecosystems, and killing large numbers of organisms across areas of tens of thousands of square kilometers. The mesoscale convective systems and organized storm complexes of the Carnian atmosphere were different in character from tropical cyclones organized by different thermodynamic mechanisms, drawing their energy from continental convection rather than warm ocean surface heat flux concentrated beneath a rotating system. Direct comparison of peak intensities is therefore not straightforward. But in terms of total water delivery, geographic extent, and persistence, the storm systems of the Carnian operated at scales that contemporary extreme weather events do not approach. A single modern extreme precipitation event, a record-breaking rainfall lasting days over a limited geographic area, delivers water at rates that the Carnian atmosphere sustained continuously across continental areas for millions of years. The storms that modern civilization experiences as exceptional were, in the Carnian atmosphere, the background condition. The question of how close the Carnian pluvial episode brought Earth to a threshold of irreversible environmental change, a state from which recovery through natural processes within any biologically relevant timescale would have been impossible, is one that current research has not answered with precision and may be inherently difficult to answer given the limitations of proxy-based paleoclimate reconstruction. The wet phase was severe by any measure. It drove significant extinction across multiple taxonomic groups, reorganized terrestrial ecosystems across an entire supercontinent, and maintained atmospheric and hydrological conditions outside the range of any modern analog for millions of years. But the Earth did recover, the wet phase ended, ecosystems reorganized, and the biosphere continued its evolutionary trajectory into the Jurassic and beyond. This recovery, however, was not a return to the pre-Carnian condition. It was the establishment of a new biological order, one in which the dinosaurs dominated, the large amphibians were marginalized, and the ecological structures of the Permian and early Triassic were permanently replaced by those of the Mesozoic. The Carnian wet phase was not a perturbation that the biosphere absorbed and corrected. It was a reorganization that the biosphere underwent and from which it emerged, permanently altered as something different from what it had been before. The stability that returned after the wet phase was not the stability of the pre-Carnian world restored. It was the stability of a new configuration, built from the survivors of the old one, organized around the ecological relationships that the wet phase had, through millions of years of selection and extinction, brought into existence. The atmospheric journey that began 232 million years ago above the warm surface of the Tethys Ocean, with the first intensification of moisture flux into an already warm troposphere, the first organization of convective systems larger than any modern storm, the first rainfall over a Pangaean lowland that would not drain before the next rainfall arrived, concluded not with a dramatic terminal event, but with the slow, continental-scale recession of water from landscapes it had occupied for longer than the entire evolutionary history of the human lineage. The rain stopped, eventually, in the way that geological processes stop. Not all at once, not everywhere simultaneously, but gradually, unevenly, leaving behind isolated wetlands that persisted long after the surrounding landscape had dried, and isolated evolutionary lineages that had been shaped by the wet phase so completely that they could not survive its ending. What remains of that world is preserved in the rock, in the coal that formed from its forests, in the fossils that document its fauna, in the isotopic ratios recorded in its sediments, and in the evolutionary heritage carried forward by every lineage that survived it. The dinosaurs that dominated the Jurassic and Cretaceous were its biological legacy. The mammals that eventually replaced them were its indirect descendants, shaped by the selective pressures of a wet world into the small, metabolically intense, ecologically flexible forms that would persist through dinosaurian dominance until the next great disruption created the next great opportunity. The birds that fill modern skies are the direct descendants of theropod dinosaurs whose lineage was forged, in part, by the selective pressures of the Carnian storms. The rain of 232 million years ago has been gone for longer than it fell, but its consequences, geological, chemical, evolutionary, and ecological, persist in the world that exists today, encoded at every scale, From the molecular architecture of circadian clock genes to the distribution of coal deposits beneath modern continents, the storm era ended. Its echoes have not.